Okay, so good morning, everyone. Thanks all for coming. Yeah, so today I want to talk a little bit about essentially some drawing techniques and ideas around using the deep neural network when your data somehow lives in three-dimensional space. And in particular, you care about that because there is some internal symmetry to the space in that there's no specific orientation in which you can look at your problem that is distinguished from the other ones. And you want to use a deep neural network that respect this fact, the fact that you could look at your problem from any direction and it would still be the same problem, so you would like the output of the neural network to be the same. So this is the kind of problem we're going to talk about today, how people are trying to solve it, what are some of the issues with some of the methods we have, what are some of the challenges you might face if you try to use those methods, and some recommendations for applying this kind of count. So maybe a bit formally, mathematically, essentially what we're thinking about today is maybe some problem that arises from physics or from some other science that exhibits some kind of natural symmetry. And by that I mean that there is some fundamental mathematical reason that underlies the problem, which says that if I look at the problem from here and from here, the problem behaves the same, except for rotating. And from a mathematical perspective, I can write this as saying that I have some underlying group G of my symmetries. So that could be the group of rotations in space, could be the group of Ridge transformation in space, or you could have some more fancy stuff like the group of Lorentz transforms if in the case with special relativity you have statistical effect on the problem. So we'll have some group G, and I know for a fact that my problem has some symmetry. So that means that when I transform my input according to a transformation, then my output has to transform in some way according to the transformation. Maybe the simplest thing would be some conserved quantity, say the energy. Like if I were to, for some reason, use a neural network to estimate the energy of my system, I'd like that energy to not change, the estimate of my energy to not change if I look at it from a different perspective. And if you think about just writing a drawn neural network, there's no guarantee for you for this to be happening. Right? A drawn neural network is just a function of all the inputs. There's no guarantee that if I were to rotate my inputs, my output will be the same. So really, the topic of today will be designing the so-called equivariant neural networks. Essentially trying to come up with a system that allows us to write down a parametric function f that respects this symmetry in some sense. So that I'm guaranteed that if I were to look at this function from a different perspective, the output will be controlled in some manner. It might be exactly the same, it might be the same output from a different perspective, whatever the exact requirement we have in that situation. Really today, even though G is in this mathematical language, this can be very vague. G could be nearly anything. Really today, we're going to focus on, I think, probably one of the most common groups G, which is the group of rigid body transforms and in particular rotation. So nearly all problems you can come up with in science essentially have the symmetry in that there's no distinguished direction in space. And so everything looks the same from all directions, and that our model to reflect this. So an example of where you can find this kind of data is so-called point cloud data. Essentially, it's a set of points, x, y, z coordinates in 3D space, and each of the point will have some attributes. For example, on the left, this is a protein. So I'm thinking of a protein as a set of atoms in space, and each of the point, of course, is the type of atom that atom is. And on the right, this is a slightly different application, but there are also applications where you might take, your phone and do a 3D scan of the room. Of course, if you do a 3D scan, then naturally what you pick up are gray intersections, which are points in space. And this, even though the underlying problem that we want to record might be a surface or something like that, the natural data we obtain are subpoints, and we now have, say, color for each point. And from there, we might want to reconstruct the surface of the point. Now, these are kind of somewhat related because they're representing 3 points in space, but also somewhat different. In some sense, on the left-hand side, what we really had is we had some underlying object from which we sample some points. We drew some points from an underlying object, but we don't believe that this shelf or whatever is made of points. That's not what the shelf is. The shelf is some kind of manifold or some mesh. We just picked some points from it because of how we tried to capture the image. On the left, on the other hand, we have a protein, and the protein is actually made of atoms on the point that's somehow like part of the object. We're going to be a bit more interested in the left-hand side because I feel it arises more often in science. Although, again, there are certainly many things I don't know about. And if you have problems that look more like the things on the left-hand side, then there's other people in graphics that are very interested in these kind of problems. Taking your phone out, trying to reconstruct the image or the surface or the mesh of something from a huge bunch of scans. Very important problem in graphics. that has a lot of applications in all kinds of domains. Okay. So the first strategy that is a little bit off the side because it's going to be a bit different from all the rest of the stuff I'm going to talk about is essentially saying that dealing with point clouds is too hard. So what I can do instead is try to rasterize the point cloud. I'm going to take the point cloud and turn it into some kind of image or some kind of volume. So I'm going to just put a grid in place, count the number of points in each grid location, and call it a day. This works reasonably well, and there have been some examples of work that have used this. So for example, you might know about the camel simulation. And in camel simulation, it's an n-body simulation. So it's a simulation where I have a bunch of particles, and at the end, what I do is I render the particles into a density field or an estimate of the density field from a set of particles, and then I can run the convolution neural network on the rendered data to try to predict my cosmological parameters or something like that. On the left-hand side, this is an example where this is a molecular dynamics simulation. So each of the particles you see, either red or blue, is actually two types of particles in a so-called Lennard-Jones glass. And what they're trying to predict is actually the temperature at which the system was stabilized. So here you have a glass state, and on the left-hand side you have a liquid state. And they have slightly different mechanical properties. And the question is, can you tell them apart by just looking at this picture? Right, again, here what they did is they just put a grid and then counted the number of points in each grid cell, and then fed that to a convolution neural network. So kind of working a little bit deeper into this cosmology example, which I think is the most relevant here. What the process was generating data from a simulated model. This simulated model is based on some n-body simulation, which is particle simulation. And then you render all the data sets as you see on the left. And then what you do is you just learn, some inference through a neural network that just directly predicts the parameters. And this is an example of, a very straightforward strategy. So it can lead to introductory results in some cases, in some other cases not be adapted, but it's something to think about. So what are some of the potential drawbacks of such an approach? The first and the main one that I think can be very constraining for a lot of applications is that it's potentially very, very memory intensive. If your data is sparse in some sense or somehow doesn't live in the whole space, and you use a rectangular grid, then the number of grid points is much larger than the particles because all the particles end up all being bunched in some places, and then you have a lot of empty space. And that can be very, very inefficient. And that is the main blocker for all of these things on the tiny to very large scale problems. You are essentially blocked in your ability to apply these on larger problems. The other problem is that there could be maybe a single grid effect. So if your grid is too coarse, then you have the impression your point jumps across the grid points. You'll see the pixels literally. If your grid is too fine, then of course you'll run into memory issues. However, it also has some advantages, which is why it's something I think you should consider if somehow you believe that the underlying object you're working with is some kind of field. So in the cosmological case, the data was points, but the points were produced through n-body simulation, which somehow are supposed to approximate a density simulation themselves. So it's kind of, we're getting back to the density, which kind of makes sense from a scientific perspective. So that is one case where you might consider. The second case is, if somehow the particles are reasonably well distributed, and you have a lot of data, this could be a reasonable strategy in that you're using these very standard, neural network building tools. You're using convolutional neural networks, and all people work on them, and they're well optimized, and they run fast, and we understand how to, make them train well and so on. And that can be a huge advantage compared to the methods linked to CNX, which can be much more finicky. And that is one of the main drawbacks. So there's something to think about that is a bit different from, most of what we're going to talk about. So I just want to just say that it's here and move on to read the main topic. So the main goal today will be to design a neural network that somehow processes data, that takes data that comes in from the point cloud and gives me back predictions on the point cloud. So it could give me a prediction which is globally for the whole point cloud, say the energy of the system. It could try to give me a prediction for each point in the point cloud. Something like what is the local charge that I here, or what is the force that is being exerted on the particle, or some of the. So in this setup, there's kind of two symmetries at play. One is this kind of SO3 symmetry. So SO3 is the name for the group of rotations. And it's essentially saying there's a symmetry in the basis in which I give you the XYZ points. if I did a change of places for XYZ, then you will see different XYZ numbers. They will still represent the location in space. They will just be different. There's a second symmetry that's a bit hidden, is that in order to write down the point cloud in, say, your computer, you have to decide on the order in which you're going to present the points, right? So, and this order is pretty arbitrary. You could present the points in a different order, and you will still get the same point cloud. It's just that the labels will have swapped, the positions will have swapped, everything will have together. So to illustrate this, for example, here, you can see that I chose an ordering like this. So this dark blue goes first, and the green, and so on. And then I could choose a different order that would have the same points, just the labels will be in a different order. And this is important because if I'm doing, say, a prediction for each point, say I want to predict that the dark blue somehow is good and the green one is bad, then here in the first position, I want to predict good and bad. But here it's bad in the second position and good in the third position. So somehow I need to ensure that my network, no matter what order I present the point in, gives me the output in the same order. So this is what I mean by SN symmetry, and SN here stands for the group of permutations on elements. So today we're going to try to work on networks that somehow handle these two types of symmetries. And we'll use from 32 slightly different tools to handle each of these symmetries. So let's first see this SN symmetry. So the form of operating data on these SN symmetrical things, and often captured as graph, is actually called the graph neural network. And there's a very large family of graph neural networks, and today we're mostly going to talk about one specific instance called a message passing neural network. So this is a type of neural network which is defined on a graph. So here I have a graph with some connections. And we're going to use the graph to somehow define both the computation. So we're going to use the graph to define what computation we're going to do. And also, we believe that the graph has some information about the underlying structure of the data. So for example, the graph, in some cases, might be very meaningful, like it might be the whole data you have. So if you have a citation network, then each of the edges of the graph can represent citations. Or sometimes the graph might be somewhat constructed from arbitrary attributes of it. For many of our examples, what we're going to do, well, there's a point cloud. There's no graph on the point cloud. There's no necessary edges. What we could do is we could try to construct edges by saying we're going to add an edge between each particle, which is closer than some threshold. In some cases, we may have both. We may have 3D information, but also there's some graph structure that is underlying it. This is often the case in chemistry and biology, where, for example, in chemistry, we know about these notional bonds and so on. And these are pretty powerful information, and you can feed your network in addition to the positions. Or if you think about proteins, proteins have one-dimensional structure that they're both a chain in a one-dimensional sequence that represents the DNA from which they were created and how the amino acids are chained together. But also they have very important 3D structure, which is how they function. So in that case, that's how both of things are. But so today we're mostly going to think that the graph is somehow given to us, and maybe we created it by thresholding the distance. So the main thing we're looking for is that it respects the symmetry of the graph. In that, when I have a graph, somehow the nodes appear in some arbitrary order that I haven't decided. And I need my network to essentially output the same thing in some sense, no matter what the order is that I give it in, as long as I permute difference. There's many variants of such, but really they all operate under more or less the same principle. Essentially, they look at one node at a time. So here we're looking at this light blue node. And what happens at this node is that we look at all of its neighbors. So all of the neighbors that have the edge that's coming to it, we look at all of their values at the given step. We can aggregate all these values together by, say, adding them. And then we transform the current value by updating it with the messages from the neighbors. So we have, in a very general sense, mathematically, what you do is we create these messages. This is a message that goes from I to j. What we say is it's some function, typically in your network. You have some freedom about what neural network you choose here, but typically this is a multi-layer perceptron, or maybe even just a one-layer linear network. And it combines the state of the node that is sending the message and some information about the edge. You might have some feature about the edge, say the distance, the length of the bond, or you might have the type of bond, or in more abstract like social networks or citation networks, this might give you a lot of information about the relationship between these two. Once you have this, then what you do is you want to aggregate all the messages that arrive at some node J. So here it's very common to use a sum over the neighbors, but you can also consider using the average, the maximum, some other kind of aggregation strategy. The only thing that's very important here is that this aggregation needs to be symmetric, right? Because you don't know the order in which you're listing your neighbors. But here it doesn't matter. If I'm summing everything, it doesn't matter which order I go through my neighbors, I will always get the same result. This is really the crucial step that ensures that everything restricts the symmetry without forcing it into existence. And finally, you want to have the message that is incoming. Very often, there's a step where I update my state at the node J by some function of the incoming message on my previous state. So this is really it's not technically necessary, but it's very, very common in that is this idea of a residual network that has been popularized across all kinds of architectures, and where I'm allowed to see my previous states and the other information I get. Okay. So just on this question, like how many people have seen a graph neural network before? Okay, so this is pretty good. Okay, so the idea today is that we're going to take the graph neural network and we're going to power it up so that it can process information, where each node is not just some abstract, citation or some abstract function or something like this, but it lives in space and is endowed with the properties of being in space. Okay, so let's try to define a somewhat general framework. It's maybe not all going to make sense yet, but it's kind of the general strategy we want to pursue. So how could we construct a equivalent MPNN? So it's a message processing network that, in addition to being a graph neural network, so it respects the symmetries of cassette, also wants it to respect the symmetries of space. So there's kind of two steps. Right? One, I need to manage a graph. Right? So I need to somehow come up with a graph from the positions. Now, in principle, I could just take the complete graph. I could connect every node with every other node. The main problem that this has is more practical than theoretical. It has to do with the fact that, of course, on endpoints, you have n-squared order, n-squared edges. And so if you imagine even like small systems require a huge amount of memory to be able to model all the pairwise interactions. And so if you imagine, so these are some examples in biology, biomolecules. If you imagine an incident, a very small protein has like about 1,000 atoms. And so you get about 1 million pairs of this. This is maybe still doable, right? Maybe 2 megabytes for the distance matrix, and if you were to do some processing on top, you could probably do it. Something like the spike protein has 20,000 atoms, and so this is like 400 million pairs. And so to store the distance matrix, you need about 1 gigabyte, and there you'd be really pushing. Now, if you had a great idea on using all the pairwise information, this is still something you could do. So, if you have a great idea on why you would need all this, then it's something definitely to consider. And there are some interesting results that people have in biology using these notions of contact maps and proximity and so on that are n-squared. So this is not something to necessarily discard out of hand, but it's something to note that it can be difficult. And the second reason we're constructing this graph is we're hoping that there's some notion of physical locality. So many systems that we study have a notion of locality where the forces that they experience decay very quickly in space. And so you can mostly predict the system from its local neighborhood. Now, this is more true in chemistry than it is in, say, cosmology, where gravity is a very long-range force, and so you might want some type of radiation. So in that case, you might want to think about maybe creating a graph that is able to have some supernodes and like a multi-pole style strategy, or there's all kinds of multi-resolution strategies that people have tried to use also. I tried to combine this. But in general, it's like a reasonable first start, and the neural network is often able to adjust for all the guesses and heuristics you've applied in designing the network, because you still give a lot of flexibility to the network to fit whatever it wants. So even though you've thresholded the forces at the distance that is not quite physical, say there might be interactions that go beyond that range, the neural network can still process it like in multiple hops. It will just get to the second part that we need to this recipe is this idea of a message that is equivalent to a set. So really what's happening is previously when we're sending and passing out messages that were just sets of numbers, they're just scalars that didn't transform in a empirical way. But in the specific context of here, working space, we would like the message that we're passing around to transform according to SO3 in some reasonable way. So here really what I'm trying to do is what I'm saying is when I create the message, so at first step I create this message that depends on my current value and the value of the edge. Then here somehow my current value has to transform under the rotations, and the edge also has to transform under the rotations. Not all these transformations need to be very complicated. We'll see a large class and quite successful class of networks where the transformation here is trivial, as in there's no transformation. We're only going to look at invariant quantities. And then also see that there's been some improvements or potential improvements where you can put in some quantities that transform beyond something that's trivial, that transform in a specific way. Maybe an example to see this will be here if you put the vector, literally the displacement vector, right, xi minus xj, the position of the sender minus the position of the receiver, then that transforms very naturally when I weighted everything. Right? It's just a difference of. So maybe we could try to put something like this for the edge, and then for each node, then we have to think of it. Okay. So before we get on with this, the question is, how do we build such a thing that transforms according to these transformations? What am I allowed to build in that? As I mentioned, for the edge, we could try to set a difference vector, and that would transform correctly. Can we set some other stuff in there? What kind of quantities can we put in there? The answer to this question essentially can be given to us through this mathematical formalism for representation. Now, it's not that important in that we don't really need to know this to necessarily use the methods here. Although they are the foundation for some of the representations we're going to choose. So let me just quickly describe it to you and then make some analogies to some stuff you might already know in terms of the Fourier transform. And then we can move on to some examples that people have chosen. So essentially, the main problem that we face is we want to construct a function, right, y equals f of x. And since we're in the neural network parts, and the neural network is typically a linear function followed by nonlinearity, followed by linear function by nonlinearity, let's think about constructing a linear function y equals f of x. Right? So I can assume x lives in some space Rp and y lives in some space Rq, and I want to construct a linear function. So there's those of those. But I have an additional requirement for that function. And the requirement is that the function is equivariant. So somehow I have some symmetry, and then when that symmetry transforms the linear space in some sense, then I want the output to be transformed in some other sense. So because everything here is linear, what I can do is I can write this transformation as some matrix. And this is called a representation of the group. And there is, maybe surprisingly, there's a pretty deep theory about this, and the restrictions that you have in the representation, the type of representations you can have, and how they behave. And one thing that comes out of this is that if you have a linear function, and that essentially respects this, it essentially commutes right with this action of the group, then f transforms each so-called irreducible representation or irrep in a separate fashion. So the easiest way to see this is really the transitional Fourier analysis you might be using. So you might know the Fourier convolution theorem, which says that if I take a convolution of signal with another, it's the same thing as doing pointwise multiplication of the Fourier transforms. Right? In this context, you can think of a convolution. A convolution, what is it? It's a linear map between two signals. Right? It's a linear operator. If I fix one of the filter, then it's linear in the signal. And it's translation invariant. Right? So convolution is translation, it's translation equivalent in that if I translate the input signal, then the output signal will be translated by the signal. So really, a convolution is a function that verifies this, where the group here is a group of translations. You can take the group translation on a circle if you want to do convolution modes. And what happens when I look at the convolution is that once I take the Fourier transform of the convolution, what happens is that there's no longer any correlation between each of the Fourier modes. The convolution literally multiplies the Fourier thing point. So what's happening is that F transforms each of the irreducible representations, which are here the Fourier modes, pointwise. It doesn't need to look at any of the Fourier modes to transform one of them. And this is important because this essentially tells us, that the linear transformations F must be quite simple once we know the Fourier modes. And there's actually a theorem that says that the converse is true, so that all the equivalence transformations must be able to be represented that way. And the important thing that we'll see here is that on the sphere, there's an analogous Fourier theory. And the Fourier modes are, rather than described by sine waves, are described by these so-called spherical harmonics, which look like sine waves. They're a little bit more complicated in that for a given frequency, there's more than one of them. Right? So the Fourier modes, there's one per frequency. Whereas here, at the frequency L, there's 2L minus 1. So that is the only difference, but fundamentally, we're doing very much the same math and the same analysis, except there's no that is the only difference. And as you can imagine, this is a way for us to build these transformations. Okay. But before we start trying to do all these fancy mathematical stuff, we can think about, pragmatic solutions. Like, we want to solve the problem today. Let's just try something and see if it works. So maybe the most obvious thing to try is just to forget that the problem is supposed to be equivalent. Right? What would happen if I just put my data into my network? I don't really care whether it transforms correctly on the XY. I'm just praying that if I do data implementation or something, then on average it will work. Right? So people have done that, and in fact, it's very successful when you do it correctly. So these two papers, both from DeepMind, do this kind of stuff, and in particular this one is one of the better models on one of the core tasks called OC20, so the Open Catalyzed Challenge. It's one of the better models that does the prediction directly. So it's not trying to model some energy and doing some optimization, it just predicts the number. Of course, there are models that are better than it, but it does better than some models that try to actually do all this invariance properly. And you ask the question, why, right? Why, given that we just said, this model is not correct in the sense that it doesn't model the right invariance. And additionally, from a statistical perspective, we know that that is suboptimal. The Rao-Blackwell theorem tells us that if the problem is truly invariant, then having the solution be truly invariant is always better. If it's not, I can actually average across modes. And my view is that there's a very simple reason for that. Is that when you're constructing these models that don't require these invariant representations, you get a lot more flexibility in choosing what your model exactly does. Right? You don't have to muck with these Fourier theories, you don't have to think about all these kind of invariants, you just build your normal neural network. And that has the advantage that there's a huge bunch of tricks that go into building neural networks that we don't necessarily have for building these invariant neural networks. But with these neural networks that just, literally put in like the XYZ differences in the edge features, they can pretty much do whatever they want. And so they get to leverage that flexibility and all the engineering that goes into neural networks to be able to build. So if you have a problem and you don't think that it's a huge issue that the invariance is not there, so basically you're just using it for prediction modes, this might be a first step you might consider. Just put the raw coordinates in there and see what happens.
So just to clarify, is your argument basically that without considering these, you can reduce the optimization error further because there are more tricks to do so? Or?
Yeah, it's hard to tell what exactly optimization error means in this context, but you get, like, if you think about deep neural network, the deep neural network is not just the model. It's the model plus the training procedure and everything that kind of goes together. And what my belief is that even though the model might not be quite as good, all the stuff surrounding the model, the training procedure and so on, gets improved so much that it compensates for the fact that you use a model that wasn't the best.
Okay, yeah, that was I was thinking about with the optimization error.
Yeah, so this is one question. There's also all kinds of other things in that we know better how to normalize these concepts. So you're less likely to have your gradient go up and reprogram to train. These might train faster until you might be able to do more hyperparameter optimization and then find better hyperparameters and so on. So that's the thing with deep learning is that because of this kind of engineering aspects, sometimes making the engineering better makes the whole difference. Yeah.
But you wouldn't expect to stay this way for very long. The fact that we have some symmetries is always good to have personal count. In the long run, like I get what you're saying, but like in the long run, I would expect that varying neural networks will go a lot better.
Mm-hmm. It's a good question. So there's a couple arguments here. One is that in the limit of infinite data, it doesn't matter whether the neural network was built to be symmetric, in that it can learn the symmetry itself. So that is something to consider. The second thing is that we're not the only one working on problems. So whilst we're trying to push ML for science, there's all the software engineers, all the people in computer vision, all the people in natural language who are trying to push their own ML models. And because there's way more of those people working on these applications than there are people working on ML science, it is often easier to steal or grab one of their models and use it for a purpose than to start from scratch.
But there are like a lot of like recently that like in computer vision people are looking at like rotation invariant, equivariant architectures as well. Right?
Yeah, it's definitely. I don't know if it will always be better. This one is not like we have some rotational equivalent ones that are better than this. So I think if you have the time and are willing to kind of tune up your model, I think you'll probably do better today with some rotational equivalent strategy. At least for some of these point problems. It's not true in general. So one example that I think of is this idea of the neural radiance field. I mentioned it during the introduction, but I don't know if you're familiar with this. So the idea of a neural radiance field is take pictures from different locations and then model my functions, like the density, essentially the light that is emitted as a function. And typically there's models of function f of x, y, z with some Fourier transforms on x, y, and z. So it's not, there's some grid and there's underlying grid, so it's not symmetric. But my problem is not pretty symmetric, right? If I took all the pictures, rotated them like this, then I would expect you to take your output and rotate it in the same way. This is not the case in the whole architecture. Yeah. There's no design for this. But also, if you think about what you need to do, design an architecture that verifies this rotational symmetry, I think it gets pretty hairy. And it seems difficult for me that it would be ever worth it for them. So I think it really depends on the context, the data you have, and a lot of things like this. There's also, of course, people who are interested in learning symmetries, and that's kind of a whole different topic. Maybe, okay, there's the spatial symmetries, but maybe there are some more conserved quantities, or nearly conserved quantities in your form that you may be aware of, maybe not really aware of, and maybe kind of letting the model try to figure all this out is better for you than, thing. That being said, I do believe that there's a value in understanding how we can design actually current ones and using them. I'm just saying it's not necessarily always the best choice, and you have to be careful when you choose the model you want to use for the task. Now, the second step, after just ignoring the issue altogether, would be to most ignore the issue, in that we still want to use our traditional neural networks. Right? But we're going to feed those neural networks with quantities that are known to be invariant. So these are quantities that don't depend on how I'm showing you the data. I just computed them to be invariant. So a typical example might be the distance matrix, right? Even though the vectors between the points depend on the rotation, the distance between them doesn't. This is conserved quantity. So I could look at the distance matrix. And if I want to, I could look at kind of some, not just two-body thing, but three-body, four-body. So very classical examples that are used a huge amount in molecular dynamics and these kind of problems be something like the bond angle. So I look at a bond ABC, I look at the angle here, and the dihedral angle. So if I have ABCD as a set of 4, then I look at the angle between the plane formed by ABC and BCD. So ABC forms a plane, BCD forms a plane. I look at the angle between those two planes. So this, in some sense, is nothing new. It's the workhorse of classical force fields in the context of molecular dynamics simulation. So people, even 40 years ago, were fitting functions of these quantities to try to predict the force or the energy of a molecular system. Right? Now, they used to maybe fit one parameter for each of the bond angle, dihedral angle. And nowadays, within your network, maybe you're interested in fitting, a million parameters for each one rather than one. But fundamentally, this is an idea that has been used a lot and has seen a lot of success. It is the main workhorse of doing simulations today is some estimates of the energy of a system based on a linear combination of these counters. So an example of an instantiation of such a procedure in the context of neural network is called Radiance. This is very successful. It was for overall one of the most successful models on predicting chemical properties in molecules. And it works by looking at invariants on pairs of bonds. So what does it do? The first thing it does is that instead of thinking of the graph as a graph that connects atoms to each other, it thinks of the graph as a graph that connects bonds to each other, so edges. Right? So you might know this as the line graph. And this is something that I want to emphasize. There's no specific reason for your graph to necessarily be the graph that you start with the points and the edges. You could think of transforming that graph, looking at the graph, the intersection between edges between themselves, and then you get more information. Or maybe even between triplets for you to get more information out of them. But this is something that comes up a lot in these neural networks, is that this notion of what people would call higher order messages, where you're not just passing messages between nodes with an edge, you're passing maybe messages between edges and between triangles and so on. So this is something that is here. I agree the two invariants I consider, one is a length one, and the second one is a dihedral angle one. So let me just kind of decipher this whole thing for you. So they're saying that the embedding for edge ji at layer r plus 1. Okay, so there's this update, and it's a residual update. So this is very common, again, across all this. And if you're doing a graph neural, probably you should consider using some residual update. So it's based on the previous value of the same thing, and then some other thing that corresponds to some notion of aggregate along the graph. And so what it's looking at is looking at all the edges, right, that come in to the start point of that edge, except the one I'm thinking about. So I'm at J, I'm thinking of the edge Ji. I'm going to look at all the edges that come from into J, but not Ji. Right? I don't want to look at the thing I'm already looking at, I want to look at all the other ones. And then what do I get? Well, I get that embedding, like the value that was on that edge. Then I get two features. These are separately computed things that depend on the physical arrangement of those in space. Right? So this is something that depends on distance. And this is something that depends on that dihedral angle. Okay. Now, the question is, why not just put the distance here? Right? Why not just put, norm of xi minus x3? And this is something that, I alluded to it a bit previously, is that neural networks, require some engineering for you to get the data into the right format for them to feel good about processing the data. And so typical strategy you might do is just normalize the data, right? Make sure that it fits in 0 and 1 by subtracting the minimum, dividing by the maximum, and doing something like this. In a lot of these things, people do something slightly more elaborate, in that they will want to break up the natural scale of the problem into different scales. So what do I mean by this? If you think of a typical neural network, right? Imagine that you just have a redo plus linear neural network. And for now, let's assume that you have no bias. Then you can work out that this neural network is actually homogeneous. What do I mean by this? I mean that when I put in f of ax, for a is scalar, I get back a f of x. Right? Why? Because the linear, they obviously verifies this, and the redo non-linearity also verifies this. Right? So I'm not saying that all neural networks are homogeneous. Of course, if you are biased, then already it's not true. But it does kind of suggest that there is a strong tendency for this linear fitting. Right? And there's no reason to believe that this thing would be particularly well suited for a linear response in terms of your distance. Right? So if you put the distance in there, then you will have to have a lot of work to break it down. Right? Similarly, what will happen is that you will essentially get a lot of leverage in the statistical system. So you might have seen this before. If you try to fit a global polynomial to a function, then a point that's quite far off, right? So I'm fitting something like x to the 5, ax to the 5 plus bx to the 4 and so on. So if I have a point where x is 100, then x to the 5 is so big that a will essentially be decided in order to make that point close to the point observed. And this is one of the reasons why it's very not recommended to fit these global polynomials to functions. And you might know rather or be more recommended to fit a spline, which is a piecewise one. So something breaking down into pieces so that my guess about one side of the domain doesn't really influence my guess at the other side. If we don't have very strong knowledge about how the things behave, often for a neural network it may be better to use, for example, here this is our RBF, a radio basis function. And what they do is that essentially they draw a little bit kernel, a bunch of grid points, and they look at which one is closest to it. So you can think of this as a smoothed out one-hot encoding of the distance between the nodes. Right? And this will really help the network be able to fit those nooks and crannies better and have better statistical behavior. And this is kind of why I said in previous part that maybe ignoring all this could be easier. Of course, nowadays people know how to come up with these kind of things, and they work quite well. But the process with which you have to come up with this can be quite intensive. And if you don't have the knowledge to do so, or if you were trying to do it before we really had good intuition on how to do this, then you might think that these things don't work as well, whereas actually they do work well. You just have to process your data carefully. A question here, for example, is for this angle. Right? So this was distance, it was a scalar, that was radiance. But now you have an angle, what should you do with it? Right? And they propose to evaluate a set of essentially spherical harmonics, right? Which is very natural. It's also related with the solution to Schrödinger's equation and so on. So there's some justification behind it, but still trying to choose something that's nice is also easy. And it's important in the performance of the network. So this is something that you should consider. Yeah, but this has been a very successful architecture and it works quite well in practice. So this is an example where I'm combining some invariants in a way that's not quite so trivial, right? Maybe the easiest way for me to combine invariants would be just to look at distance matrix and try to process the distance. This is something that goes a little bit beyond that and looks at some angles and so on. And so it's a good way to, if you believe for some reason that angles are very important in your problem, this could be something that you look at. Again, in cosmology, I don't know how often that happens since gravity doesn't really have these features, but in molecular dynamics and these kind of problems where there's extrinsic interactions, there are some important angular effects that people have designed these. Finally, you say, okay, well, if invariants are not enough, right? I would like, know that there's the length and then there's the angle and there's the dihedral angle, but what if I want the neural network to figure out what is important in those things, right? So that's what we do for an image, right? If you think about an image and a convolutional neural network, we don't try to feed the neural network. Okay, here's the filter that does the edge, the filter that does this edge, and so on. We just figure out the filters, then what's important, and then we're going to train, and you're going to figure it out, and we're going to use those. We don't try to hand design filters because data is much better than humans at figuring out what is important. Okay. So here, in some sense, we want to bypass the need for us to hand specify what invariants they are, and specify filters, just say learn filters and draw sense, and hopefully. And this is really where all this robustness really could come in and help us. So once we go into what so-called sometimes higher order representations, well, we really want to actually model something that is not just invariant, that actually transforms with the rotation. Then we go into something that's a bit more mathematically complicated, a bit more computationally complicated. So now the main thing is that the activation, right, the message you send is really a function on the sphere. It's something that transforms with the rotation, so you can think of it as a function on the sphere. And of course, there's no way to write down the function. Right, function is this infinite dimensional quantity. You cannot write it down directly in it. So you have to choose some way of writing down a function that is n-dimensional so that you can code it. Right? Some kind of basis or some other representation. Right? So there's two natural ways that to map a function in space. Right? So one is I could try to use a Fourier basis. So I could encode the function as a sum weighted sum of spherical harmonics. But this would be very similar to you encoding a function on the real line using its Fourier decomposition. Right? If your function is very smooth or something, this could be a good choice. The other thing you try to do is just encode the function using the spatial basis, right? Using the sample points. So this is like you encoding a function on a real line by sampling some points or having a grid and remembering the value of the function on those grid points. Right? So this requires sample function the number of points in the sphere.
I didn't completely get that first thing, that the activation is now a function of the sphere.
Yeah. So this is a little bit tricky to kind of explain abstractly, but essentially it's a mathematical formalism to just say that the message I'm giving to you is not something that can be represented as a function of the sphere. It's a way to capture any kind of translation, any kind of thing that transforms according to the rotations. I can eventually write down as a function of the sphere because the sphere is the homogeneous subspace of this. But the easiest way to think about it, if you think about what we just did before, how is what we just did before a function of the sphere? Well, the thing we just did before is it's a function of the sphere because it's the constant function of the sphere with the invariant being the value. Right? So when I rotate the sphere, the function doesn't change at all. But you can imagine a more kind of tricky function where it's just a vector. So the function of the sphere is given to you by, say, a Gaussian centered at the point. And now when I turn the sphere around, this whole function changes in the correct way. So in general, like this kind of generalizes to all kinds of functions. And it's kind of the most general way to talk about a message that transforms according to the rotations. So here are some examples of strategies that have tried to use this and kind of the type of problems they have encountered. So Cormorant is a architecture that some people here developed now 3 or 4 years ago, and it's based on a purely spectral representation. So it's like you going ahead and deciding, okay, we're going to work in the Fourier basis. Right? So I'm going to just look at the Fourier coefficients, and that's the only thing in spectrum. So on the sphere, so here is my activation, HA. So it's a function of the sphere, so it takes as argument the direction. And I'm just saying that it can be written down as this sum over the Fourier series. So this should be little else. But it's just a sum of these spherical harmonics, which are functions, a big set of bases, right? So it's a sum, these are the coefficients, this is my basis, and this is what we're going to work with. The main trick that we're going to do here is that there is, in fact, a way for us to write down the coefficients of this function, which is the product of these two functions. So as you can imagine, if you think about this traditional Fourier transform, this is maybe not that surprising, right? I mean, after all, you just look at the product of these types of things, expand everything, you get a bunch of coefficients, and then you get the product of 2 of your basis functions. But because they're basis functions, you can write the product of 2 of your basis functions in terms of some other expression in terms of your basis. You write everything else, and there are some mathematical forms in how you do it, the so-called Kepler coefficients and so on. If you find with like more quantum mechanics and so on, they appear quite commonly there. And you can write these down. And this is really the main transform we're going to use. So we can kind of model this into some message expression scheme. But what we're saying is now it's in some sense a bit simpler than what we've seen before. It's going to say the message at point B is a function of a sphere. And if I evaluate it in the direction r hat, what is it? It's the sum over the messages over the neighbors of B, so where it comes from, some edge activation, which again, we're keeping everything as functions on the screen. So it's the activation of HAV, and then YM20. So in some sense, by turning ourselves up to this formalism, we simplify all things. But the truth is that we just hide everything behind the complexity of computing. Right? These operations are significantly more expensive. We're reformulating, we're doing a change of basis, and then we're expressing the product of two basis functions in the new basis. So these operations are simply more expensive at the expense of us essentially having something that's a bit more general and that much more. So this was quite successful on some small molecular problems. It has some issues that we'll discuss later, but this is one example of a strategy that you could.
This is like a generalization of like a standard Fourier kind of doing convolution in the Fourier space.
Yes, exactly. So you can do convolution. So here I didn't show it. There will be convolution here. But the main thing we're doing here is we're taking the product of two functions. So you can imagine, if I give you two functions in Fourier space, you can take the product of them. Right? And then you will use the trigonometric rules to rewrite sine x, sine like kx, sine lx into a sum of sine k prime x. And then you will figure out the coefficients.
Here you're kind of like limiting like the frequencies, like the coefficients you're looking at.
Right? Yeah, you will have to cut it out at some point. That's a very good point. So these will have very high frequencies, right? And if I don't stop looking at it, then it will get higher and higher and higher. Right? And then it's too much compute. So I'll have to cut it out at some point.
And so because you do it in the Fourier space, you're guaranteed to be correct.
Yes. Yes, this is one of the main things is that it's very natural in this space for us to be correct. Now there's some issues. For example, one question is, can you come up with a nonlinearity in this space? That is strict. A nonlinearity in spatial space is easy. I can just apply pointwise to the function. I'm guaranteed to be correct, right? Because I have a function, I just change it point by point. The function still changes the point. In Fourier space, finding a nonlinearity is a problem. So in this work, what they did is they used this to create a nonlinearity. And with this, you can create a square. Right? If I put a and h here, it becomes HA squared. That's a nonlinear transformation of h. So I can use this, but as you may or may not know, using a square as a nonlinearity in general is not the best idea. It doesn't have quite the right properties in that, it can blow up quadratically and so on. You see it's only linear, so that's a bit bad behavior. So that is one of the issues that these types of strategies face. That is not quite resolved yet. And the last thing I want to mention is this GenNet, which is another approach that rather tries to use the spatial representation. So instead of trying to represent the thing as a function on the sphere using Fourier coefficients, it just samples some points. And yeah, so the image expressing is fundamentally the same. It looks at the current function, and then it looks at all the neighbors, and then at their value, and then it just samples somewhere in delta. The main thing is that this function, so in the previous slide, HV, we had it written out as some set of Fourier series, some set of coefficients times the spherical harmonics. Here we're going to take a very different approach. We're going to just write this out as a sum of essentially direct deltas in the directions of the neighbors. So for each of the neighbor, that defines the direction, and I'm going to remember some value for that. And then the function will be 0 everywhere else. So this function essentially just lives on the three directions where I have neighbors, and then is 0 everywhere else. Yeah.
So this question about the last forward, that is actually not invariant, right? It's actually equivariant because you rotate everything.
Yes. From a mathematical perspective, covariance is a general case of invariance. So if you want to read something invariant out, you will have to read the L equals 0. The L equals 0, 1 is invariance. So there is one way to do it. These two things are kind of covariant. So you see this one also, or the whole thing was talking about the thing with invariance is that even if your problem is invariance, you want your layers in the middle to be covariant, right? Otherwise you lose something, right? If you force each one of your layers to be invariant, then you're erasing out information at each layer. But if your problem is truly invariant, then at the end you will need something invariant. But what is often preferable to do is use covariant layers that all transform together, and at the end somehow average out, reduce to something invariant. If you do it at every layer, then it's a bit pessimistic. Okay. So here is a kind of this spatial tracking, and then it turns out that once you do out the map with this direct delta, it all cancels out into something that only depends on the directions of the neighbors.
I'm a bit confused about the notation here, right? H here it's different from the H before.
It's the same in principle, but the H before was written in this Fourier domain. The H now is written, the basis, you can think of this as the basis. But the basis are just direct deltas in the direction of my neighbors. So it's not really a basis, it's just some point of something. And I'm giving them some coefficients, which are called HAT.
So these coefficients are learned, or are they like?
They're produced from here. So you can imagine that there's some initial MLA that produces HA at the layer 0. And then at the next layer, the way I get there is I look at this. So essentially, I look at this. But this tells me the next layer is this layer plus the sum of the neighbors of their activation of the neighbors times some variant function that has something to do with the difference where I am and the direction. And that's right.
And this F sphere is what exactly?
It's some learned quantity that controls how I'm transferring. Like it has to do with the edge. You can think of it as this.
I see, but you have to make that also equivalent, right?
Yeah, you have to ensure that this is correctly equivalent. Yeah, there's all more details in the papers. Like these are kind of,
yeah.
As you can tell, and that's one of the reasons why I suggested that if you don't need to reach for these things, you might want not to. Is that as you get into these higher order things, they become like way more complicated. Like there's way more stuff here, just not just mathematically, but also when you go and code these things up, there's way more code. And that is, I think, a reason to be careful when you use it. Let's not say don't use that. Is be aware that you're getting into these more complex models that have more moving parts. They gain the ability to distinguish some more interesting angular forms, and if those features are important in your work, then there might be a help. But they also, from an engineering perspective, from a mathematical perspective, more complex, and that's something that I think you should think of if you're using your model to do science. Right? You're trying to solve your problem. Your problem is not necessarily building the next equivalent model. So find a model that works. So just to finish off some kind of reflections on these type of models. One is the space representation, right? If you try to represent something that is not a scalar, right, something that transforms according to the rotations, then you have to choose some way of representing it. That your choice has an impact on both the memory and the control concept. Also, it influences something quite important that influences how you choose your nonlinearity. In structural space, even though the theory is very elegant and somehow it's very nice to write down, it's very hard to write down good nonlinearities in spectral space. And one of the main things that, if you were to do this, that you want to, is your nonlinearity should at least mix the different Fourier frequencies. So that's, if you try to design some new nonlinearities, something. Finally, some last practical issues that come up, and I just want to stop it there. One is that encoding is super important. The way in which you put in your value, right, x, you might not want to put it in the x, maybe you want to put it in as a Fourier series. Maybe you want to put in a value on some kernel. This can make a huge difference in your ability to train your model. Even though, if your model is large enough, in principle it's equivalent. It makes a huge ability it makes a huge difference in your ability to train the model, and it can make a huge difference in the results you get. It's quite restrictive when you're trying to do these higher order things with equivariance, right? When they don't need to be equivalent, you can use whatever trick you want. When they need to be equivalent, you need to be more careful, and that can be restricted. And some of the classical tricks you might know, like encoding a Gaussian RBF or some Fourier kernel, might not work so well. The second thing is normalization. Yeah.
So, like this positional encoding stuff that people use, there might be some nice way of generalizing this to like equivariant, right? So the problem with these techniques is that they're not equivariant by design. But if you come up with like an equivariant encoding, then that would also.
Yeah, it just happens to be funny. It's not completely clear how to do that. There. The second problem is normalization. Again, if you have a somewhat deep network, normalization, you might have a batch norm, layer norm, and so on, are very important tools for you to be able to train your network. If you remove them, most likely your network just blows up. And it's again not super clear how you can normalize something that is SO3 equivalent, right? Like, okay, what do I do with it? Now you could try to say compute the global norm of the SO3 vector and then normalize by this. This is still correctly covariant and so on. So this is fine. But is it exactly the right thing to do? It's hard to tell. We don't have as much experience and so on about tuning these kind of architectures, and we don't exactly know what the right normalization to use. Same thing, you need to make sure that initialization is correct for all your layers. So you might know that now today, if you write just NN linear or in Python, so declare density and TensorFlow, you get a default initialization, probably Hamming-Hay initialization, which is based on some argument that if you feed in white noise to your layer, then you get about white noise out. So the variance is about preserve, which makes it so that we're hoping that the gradient doesn't vanish and doesn't drop. And this will be the idea. Now, when we use these kind of difficult encodings and when we try to use layers in these kind of equivalent ways, then this argument may not hold. The type of values you're computing might not be mostly kind of Gaussian zero. And so you might need to adjust for that. And in particular, in the last paper, GemNet, they run empirical calibration to figure out what variance they need to use for the initialization. So they literally run some data in, look at the variance, and then set the variance so that the data they run in has the same variance. So to finish up, I would say my recommendation is to try some invariant methods first. They tend to be easier, they can get you started more easily, and they're still on the basis of interesting problems. If those don't work, and I think only if, you can consider higher order methods. But I would say I would only consider them if you think it can be much better, or if you have some insight into the problem that tells you that there's some notional angular aspects that is not captured by your invariants. So that's it for me. Thanks.
In AlphaFold, they also do some kind of form of equivariant attention.
Yeah.
Is that similar to the techniques?
The AlphaFold problem is interesting because, in principle, AlphaFold is not really an equivalent problem because the input doesn't transform, right? The input is a sequence. Right? The type of equivalent attention they use is very interesting, actually. What they do is, when they do the attention query, they output a vector in the local reference field. So they locally they come up with some notion of frame, and then they output the vector there. And then once you have the vector, then you can transform it accordingly to all the other frames. This is something that I haven't really seen any really similar things before or after. So it's not completely clear how well it works or how it works. I have to say, AlphaFold has off interesting engineering decisions, and it's a bit hard to tell whether they're important and how to replicate them. They did do ablations, and overall, it seems that they're not so important one by one, but they contribute a bit, but not that much. They're also incredibly expensive. AlphaFold has triplet transformers. They have transformers that work on triplets. So it's like an n to the 6 or something scaling. And that is incredibly expensive for most of us to run. They, of course, have our resources to train their model, but I think, typically in the academic environment, we're constrained by the amount of resources we have to train our models. And some things that they do, I don't think are quite realistic for us to do, unless you somehow get access to a huge amount of resources. So that's something also that is not clear to me, since I don't really have a way to evaluate it. I don't have a nutrition.
I think last year at CVPR, there was a paper that does something similar, like it outputs like a vector. I think the paper is called like vector neuron, but they don't. It's like for computer vision tasks like segmentation and so on. So they also have to redefine like the definition of like non-linearities, like relevant stuff is not equivalent anymore. So you have to do it like kind of like project the vector onto like a half plane and so on. So you have to like kind of redefine everything.
Yeah, you have to fix a lot of things. Redo is working on. Actually, redo is not. So CNN that's supposedly equivalent to the thing. But if you apply a redo, it's no longer the case. I mean, it's equivalent to full pixel shifts, but not to sub-pixel shifts. Whereas in principle, a conclusion is equal to subtextual shift if you define what a subtextual shift is correctly. And the reason is that the redo is not band limited as a function. Right? So if you view the whole series of things in spectral space, right, then there's no problem with subtextual shift. You just shifting one thing. But if you have redo at each step, then you're going to face aliasing issues because it's not band limited. You're not limited. So there are all kinds of problems like this that people can fix, but there's a lot of details. It's not clear, like whether this is a problem or not depends on the problem. I don't think for all problems you need to be exactly equivalent. For some problems, it might matter more. For example, if you're running your whole thing through an integrator at the end, and you're going to repeatedly query your model, for example, and integrate, solve some different equation based on that output of the model, then it may be very important that you preserve some quantities exactly. If you're just using it once, then maybe the statistical equivalence is enough. You're approximately equivalent, but not exactly, but it's fine. This is something that people have seen in, say, collection of forces. So in the force field, where you want your force to be conservative, so you want the force to be the gradient of some energy. And if you're integrating with respect to the force, it's very important that that's the case, right? Otherwise, you don't conserve energy in the system of situation. But if you just want to predict forces, then actually, people have seen that in some cases it might hurt you to try to model the energy and the gradients. You might be better off trying to model the forces as things that you predict directly rather than trying to predict them as gradient of some energy. So again, this is a very new field. Maybe we'll have better solutions in 2 years, but currently it's very hazy what is the right way to take.
I have a question that's kind of related to my earlier question. So in positional encoding, they don't embed the invariance maybe that you would want in the problem, but there is it is invariant. Every coordinate is invariant to a different frequency. So there is some invariance there that might wouldn't they maybe also help the
network? Yeah, that's a very good point. There's some translational invariance.
Yeah.
But generally, I didn't talk about translational coverage today because generally people don't. It's very easy to solve it. You just take differences, and everything will be translational coverage. The main kind of thing that it's not equivalent to is rotations, right? And rotate especially non-axis line rotations, because when I take XYZ and transform into some kind of thing, then the Fourier grid shifts. But the question of whether we can fix this and whether it is worth it to fix this, I think it's very open. I think currently my impression that it's probably not worth it to try to fix this kind of stuff. It's not really the bottleneck in the method. So. Yeah.
Another kind of limitation I feel is that you need kind of rich feature spaces, right? You can't really do equivalent field networks on pixel observations, for example. At least I'm not familiar with any work that can actually build these kind of features and then transform them. All of these works that focus on molecular factors where you already know this is the position, these are the angles.
Yeah, I think you need point outs for those. So the issue with equivalence is that equivalence requires you to be equivalent to my modeling. Suppose you have a statistical model where you get px, p of y given x. You see y, you want to infer x. And p of y given x is invariant or equivalent. But if p of x is not invariant itself, then you count the inference procedure is not invariant because there's some bias due to the prior. And in all of these image things, there is bias due to the prior, right? You take images from kind of a preferred position. We've actually seen this even in some simulation things where essentially there was a bias in the position of the thing, so the problem was not invariant. And you would do better by remembering that position. So definitely this is something that also can be an issue. And yeah, if the problem is not exactly invariant currently, it seems that you're better off kind of ignoring it. But my belief that this is due to these engineering issues. It's not fundamental to the method. It's due to the fact that once you committed to designing, you might need to pay from all these engineering issues that slow you down and make it more difficult for you to fit that you could avoid. And so you have to kind of really think that it's a big deal in your case for that to be worth it.
But I don't know, it seems like, at least to me, a bit promising, like, like computer vision, detectors, right? Like when you're looking at like a chair, and we slightly rotate the chair, like the predictions start, it's quite fickle, right? It seems like this seems like a natural way to kind of solve those problems. Like you're guaranteed that if I rotate the chair, if I move the chair, the sound will change.
Yeah, I think that is both the upside and the downside of this. Is that partly you might think that being able to be very fickle allows you to fit a large variety of things. It makes it more easy for you to kind of fit different things and get close to the truth. Whereas if you're very stiff, you become very underparameterized. I think that also has to do with this notion of overparameterization. There's some sense in which being very overparameterized helps you, find the right answer. Whereas if you already encode some of the numerics in, then it might be more difficult for you to get to it. There's even like kind of there's an optimization issue also I have in that if you think about constraint optimization, a modern constraint optimization problem does not enforce the constraint necessarily all the way through the optimization. If you think, I have a constraint optimization or a constraint of something like this, then it might be worth for me to come jump across my constraints and then towards the end enforce it. And if I have an Lagrangian method, it comes this naturally, my trade-off between my constraint being, fixed and now objective. And I think this type of issues can also arise here. If we fix the constraint that's exactly invariant, then it might make the decision harder for us because as we can proceed through things, we can only try out hypotheses that invariant, and this might not be the best thing to try out at this time. Again, these are all very conjectural. It's not clear what the issues are exactly, but I almost say there are some promises, but there's also issues.
Okay, so let's thank Wendy again. The next talk, okay.
Yeah, happy to introduce Xavier for his second talk.
He's not working.
Yeah, I don't know what's wrong with it. I'm gonna have to contact AV about that.
Just turn your heads to this one for now. Yeah, you can move closer if you want. Okay, yeah, you're free to start.
Okay, yeah. Okay, well, so today we're going to continue a little bit on what we had been doing last Friday. And also a little bit along the lines of what we discussed and some of your questions. That was, well, it seems like the optimization landscape is very messy. What can we do about it, right? So I'm going to be talking a little bit about natural gradients, which is something that I find very interesting in this context, but also can be applied more generally. And then we're going to start discussing fermions because electrons are fermions, and they do require some very specific. Essentially, the wave function has to be antisymmetric with respect to its input. So we're going to see how can we do that, why that happens, and then we're going to use that to simulate a couple of interesting physical models. One is something that condensed matter physicists are very interested in, which is the Howard model. And the second thing, we're going to compute the dissociation curve of an H2 molecule, again, using these neural network representations of quantum states. So again, I've sent you the Jupyter notebook in case you want to follow along. If you want to follow along, you're going to have to run this first cell to install Netcat and PySCF. PySCF is just an open source library to do quantum chemistry calculations, and we're going to use PySCF to extract the Hamiltonians for the molecules that we're going to be solving, essentially. If you run this cell, probably you may want to remove this quiet flag, so then you are sure that everything is getting installed properly. But yeah, and then you can just run the third cell to make sure that, in particular, Netcat has been installed properly. Okay, so we're going to begin by talking about the stochastic reconfiguration. This is what in data science they call natural gradient. Actually, two people came up with the same idea in two very different contexts. Amari came up with it in the context of optimizing probability distributions, and at the same time, Sandro Sorella came up with the same idea to optimize wave functions. And I think the papers came out exactly the same year. So it's a really very funny coincidence. But okay, now let's review a little bit of regular gradient descent, right? In regular gradient descent, we all know that the upgrade rule for the parameters, so how we change our parameter theta k, is given by minus a learning rate, which in this case I'm calling mu, and then the partial derivative of your loss function with respect to that parameter, okay? But, well, here what I'm calling, so essentially, so theta k on the t+1 optimization step is given by theta k on the previous optimization step plus this delta theta k. But actually, I think it's interesting if we see, because actually, when I learned about this, gradient descent, which we always learn in undergrad or something like that, okay, they just tell you that's the update rule, but you never actually learn where it comes from. And you have the intuition of, I'm just descending along the direction of the gradient. It makes sense, intuitively makes sense. But what are the underlying assumptions of this update rule? So we're going to actually go through the process of deriving this update rule. Now, okay, now we know that we want to optimize this loss function in E of theta, where theta is the set of variational parameters. Saying that my internet connection is unstable, so hopefully this works, but it's fine. Now the goal is to find the values of theta that extremize my function in theta, and that happens when the partial derivative with respect to theta p theta is equal to 0, right? But I'm going to rewrite this in terms of infinitesimal increments, right? Here, big delta theta is what I'm going to call E theta plus delta theta, so small change in the parameters minus E theta. If I tell or expand E theta plus delta theta to first order in delta theta, what I obtain is E theta plus the sum over all partial derivatives of E theta, and then this delta theta k. And then I obtain some order delta theta k square terms, which I'm not going to be too worried about. And then here I'm removing E theta from this expression, right? So, I mean, this is just to say that this change when I change infinitesimally my parameters is simply given by the derivatives multiplied by the change of delta theta k. Okay. And what I'm looking for is where the partial derivatives of this thing is equal to 0, but in this language of infinitesimal variation of the parameters, that's equal to when big delta theta equals to 0, okay? Which corresponds to having an extremum of the loss function. Well, I mean, you can, of course, always fall within a saddle point, but that would be very unfortunate. The other condition that I want to satisfy is that the distance in parameter space between the parameters before updating the parameters and after updating the parameters, that's small. And one way of quantifying distance, why not, is the square of the distance is just the sum over k of the variation of my parameters squared, right? Yes.
Why would I want the distance to be small?
Well, because I mean, intuitively, you don't want to be making huge jumps, right, on parameter space when you're following a gradient descent type of optimization. That's sort of the argument that you would use, right? Because if I make too big of a jump, then I might end up completely overshooting my minimum, for example, right, that I'm after. So that's one underlying assumption of this gradient descent update rules, is that on top of wanting to minimize this change when I change my energy, is that I also want to minimize the distance between parameters, and it's just an assumption. And one way of quantifying distance is just the Euclidean distance in parameter space, because why not? When I don't have any other information, that seems like a reasonable assumption to take, right? Now we want to combine the notion that I want a null change on the energy when I obtain my maximum or minimum of the function when I change parameters, with the notion that I want to be doing very small parameters. So in order to be able to find what is this delta theta k, what I'm going to say is, okay, at the end of the day, what I want to minimize with respect to the change of the parameters, okay, remember what I'm trying to find here is how I change what I want to find is the delta theta case, okay? So I'm going to try to find the extremum of this objective function, which is the change of the energy when I change delta theta k, and also with a Lagrange multiplier lambda, the distance in parameter space. So this gives me this objective function, right, which is the partial derivative of the energy function. In this case, is energy, it could be whatever loss function you want with respect to theta k, then the infinitesimal variation of the corresponding parameter delta theta k, and the distance in parameter space multiplied by my Lagrange multiplier. Now, the minimum of this objective function, well, I just find it with respect to delta theta k by taking the partial derivative with respect to delta theta k and setting it equal to 0. When I take the derivative with respect to delta theta k here, well, this term essentially just selects whichever component I want, and then this one, of course, lowers the squared in the derivative, so I end up with a linear function on delta theta k. And I can solve it, and actually, and the solution is that delta theta k is -1/2 lambda delta, the partial derivative of the energy with respect to theta k. So we've derived the update rule for regular gradient descent, and the underlying assumption was I'm also minimizing the distance in parameter space, and the distance is given by Euclidean distance in parameter space. This is very important. And now you can see that the learning rate that one sets as a hyperparameter when you start doing this optimization is nothing but the Lagrange multiplier that you've put, well, it's related to the Lagrange multiplier that you put in this objective function, okay? And again, it's interesting that, well, when you put a very small learning rate, you're expecting to have very small jumps in parameter space, right? But a very small learning rate means a very large Lagrange multiplier. So in this objective function, that means that you are prioritizing having small steps in parameter space as opposed to prioritizing having this condition here. Now, but okay, coming back to the case of wave functions, yes.
What's the intuition? I don't understand that point of like why a small learning rate would give you a big Lagrange multiplier. Why is that?
Oh, I mean, if you, so this is the regular update rule of regular gradient descent, right? Where mu is the update rule. Now, if you go back and follow the logic that I did, now lambda is the Lagrange multiplier here. If you follow the math, what you end up is with this update rule, which where you can just identify the learning rate as 1/2 times the Lagrange multiplier. Okay, that's cool. Great. So okay, but that was in parameter space, but how does that translate into wave function space? Well, actually this assumption of wanting to move very little in parameter space might be completely wrong in wave function space. And let me run you through an example. Again, this is a two-level system. This is spin systems that we were looking at last Friday. And I'm going to consider a parameterized function, which is the normalization factor, okay? Theta 1 is the first parameter, 1 plus sigma over 2. Remember, sigma could be plus or minus 1, depending on the state of the spin. And then I'm going to apply this type of sigmoid function 1 over 1 plus exponential of a huge factor here, multiplying my theta to my co. Probably I should make this a little bit bigger. Okay. Theta 2, my second variational parameter, 1 minus sigma over 2. This means that the first component of the wave function is simply dominated by theta 1, my variational parameter, and the second component is dominated by this sigmoid function, right? And let's say that we are beginning in a parameter configuration in which both theta 1 and theta 2 are close to 1, right? So if I plot both wave function components here, so phi 1, the first wave function component, as a function of theta 1, well, I see that it changes linearly, right? Just simply because that's the way I constructed it. Now the second one, even when theta 2 is equal to 1, well, it changes extremely rapidly close to the parameter choice that I had. So here you can see that intuitively, a small change in parameter space, what does that even mean, right? If I say that, okay, delta theta equals to 0.1, fine, that's a very small move here in the first wave function component. But in the second wave function component, it's actually going to set it to 0 if I move along the negative direction, right? So that's a big change in overlap between the previous wave function and the new wave function once I update my variational parameters. Yes.
So yeah, I mean, I get in this example, like it's the theta 1 and theta 2 are very different influences.
Yes.
But like normally, is it like this is kind of like an
you think it's like a fabricated example?
Kind of. Yeah.
Sure. I mean, that's a fair point. It's definitely a fabricated example to find one of these conditions, but actually in the usual parameterizations that people use, the neural net parameterization of these quantum states, there's a bunch of exponentials of things.
Okay.
So it's not so weird to find yourself in a situation where something like that happens, where one of the exponentials, one of the components is given by an exponential of something that is multiplied by a small prefactor, so that's essentially linear in the parameter, whereas the other one is multiplied by a huge prefactor, where this is essentially this sigmoid type of thing. So it's not so uncommon to find yourself in a situation like this, actually.
Okay, so like especially because we like our model is kind of inspired by this quantum physics kind of considerations, which is why.
Well, the thing is that one of the things that when we use these neural network parameterizations of quantum states, I mean, this is kind of like something that, you know, we wish it wasn't like that, but sometimes we don't have a lot of control over how the parameters actually change the different wave function amplitudes. So a situation like this can happen, it's common, okay? So we should be careful about it. But again, I'm talking about wave functions, but the same type of notion can apply to probability distributions, right? When you're trying to match probability distributions. Yes.
So the natural gradient here, you're basically just taking the gradient and.
Well, I haven't gotten to natural gradient.
Oh,
yes.
Okay.
Yeah. So that was just to showcase, okay, if I move with regular gradient descent, I might end up with very pathological situations here where the wave function component changed very differently based on how I change my parameters. And also as an example here, I've set up some functions that compute overlaps between the wave function where both parameters are 1 and the wave function as I change the parameters via delta theta, both of them. So we can see what is the overlap. Now, if I change delta theta 1 from 0 to 0.2, well, this is a very small change in the corresponding phi 1 amplitude, right? So I expect that if I just move along the theta 1 axis, the overlap is essentially not going to change. Now, if I move along delta theta 2, as I said here, you see this humongous jump in one of the wave function amplitudes, which translates into the overlap decreasing extremely quickly. So if you say, okay, here it seems reasonable to set a learning rate of 0.1, well, it's reasonable along the first parameter axis, but it's completely unreasonable along the second parameter axis, because now if you say delta theta 2 equals to 0.1, the overlap with the previous wave function is very small. So this motivates us to come up with something better, right? So how can we solve this issue in practice? Well, let's come up with a notion of distance in parameter space, which makes sense when it comes to wave function overlap, right? And you know, wave function overlap is simply the inner product of two vectors, right? So it's the length of the first vector times the length of the second vector times the cosine of the angle between both vectors in the vector space, right? But both vectors are normalized, so the lengths don't matter too much. So what matters is simply the angle between these two vectors. So why don't I just consider the distance between two wave functions to be between, so with parameters theta and theta prime, to simply be the arc cosine, so the angle between these two wave functions with two different parameters. This is something that makes a lot more sense, right? But now the thing is that the infinitesimal line squared element becomes a little bit more complicated. Before it was just delta theta k squared, right? Now, to derive the infinitesimal line element, I have to be a little bit more careful. I have to tailor expand this arc cosine and also the wave function amplitudes. But in all of the cases, when you come up with the infinitesimal squared line element, you're going to come with a quadratic form here on delta theta. So where you have a matrix which is multiplying delta theta I, delta theta j. Okay, so this is just a quadratic form. And you expand things so you find quadratic form. Now, the particular matrix that enters this quadratic form, just after doing some very boring algebra, is simply the real part between the overlap between the wave function when I change parameter along direction I, and the overlap when I change the wave function along parameter j. And then I have to remove this product of overlaps where I move when I compute the overlap between the wave function when I move along parameter I with the original wave function and the original wave function when I move the wave function along parameter j. So now I can plug this in the same objective function that I used for regular gradient descent, but the only part that is changing here is the d squared. Now the d squared is going to be this k prime. This g is the metric tensor derived from this notion of distance in parameter space. Okay. Before the metric tensor, for those that do special relativity and stuff, before it was the identity. Now the metric tensor is given by this expression here. And we just find the minimum by taking the derivatives, putting them equal to 0, and you find this other uptake rule. Now it's not that, you know, this is regular gradient descent uptake rule where delta theta k is equal to -1/2 times the Lagrange multiplier, the derivatives. Now you have that the product of the matrix by the vector of changes of parameters, if I put this in a vector, so that would be a matrix vector, equals to -1/2 times the Lagrange multiplier the vector of derivatives. Okay, so this is a linear system of equations that I have to solve to be able to find how to update the parameters. So you see that this is more costly in terms of computations, right? You can, of course, just try to invert this matrix and multiply it by the vector of derivatives, but that turns out to be much more numerically unstable than just solving the systems of equations. So this is what natural gradient is in the context of quantum states. In the context, for example, of probability distributions, here you would have the KL divergence between two probability distributions or something like that. So let's see how it actually works, okay? Let's come back to our example of a simple spin on a magnetic field along the x-axis, and the same wave function ansatz that we used yesterday. And now I'm going to use netket to solve this problem. So I just have one spin. The Hilbert space associated with a single spin is being defined here. And I just define the Hamiltonian with sigma x, the sigma x Pauli matrix. I defined the wave function using Flux as we did last Friday. So, but again, it's relatively simple. I say that it's the cosine theta 1 times 1 plus sigma exponential theta 2 1 minus sigma. I'm just telling it to return cosine theta 1 here instead of sigma. I'm calling it x. Fine. And the exponential of theta 2 times 1 minus x. And remember that netket is expecting not the wave function amplitudes, but the logarithm of the wave function amplitudes. So I just say logarithm of the wave function amplitudes, and that's it. That's what our model is returning. I'm also here defining the parameters, and this is one way of defining the parameters. We can set this variable self param that comes with the Flux interface, where I'm just label the parameter theta 1. I use a function to initialize it, so from a normal distribution, and I tell it what dimension this parameter has. In this case, it's a number. Theta 1 and theta 2 are both numbers. So, right. I define this. I print what the output of the parameters are. So theta 1 and theta 2. Now I'm going to initialize them by hand. So I'm going to start the same optimization both using regular gradient descent and natural gradient. Okay. So I'm going to store what is the initial value of these parameters. Test that things are working properly. I'm also going to ask it to compute the expectation value of the energy of the system with these initial parameters, which is minus 0.001 or something like that. Remember that the ground state energy is minus 3 in this case. And I'm just going to run regular gradient descent, right? So here I have two lists, one to store the energy on each optimization step, another one to store the parameters on each optimization step. First thing that I do is I store the parameters on each optimization step, compute the energy and the gradients of the energy, store the energy, update the parameters according to gradient descent update rule. So your new parameter equals the old parameter minus 0.01. Here in this case, the learning rate is 0.01, right? And I'm going to do the same thing using natural gradient. Again, something to store the energies for the natural gradient, something to store the parameters for the natural gradient optimization. The only thing that is going to change now is, again, I'm asking netket to compute energies and gradients, and I'm storing the energies. Now, here, the variation state object of netket has a method that computes the metric tensor for your corresponding wave function, right? And this is going to return a matrix in this case. Well, it's actually going to return another object that has other methods, so you don't have to solve the system of linear equations by hand. But essentially, this quantum geometric tensor has another method, which is to solve a system of linear equations of the types of that I showed for parameter update. So you tell it to solve a system of linear equations where what you have on the right-hand side is the gradients of the energy. So it's going to return the solution, which I'm calling delta theta, and then some information on the actual solution. And then we can update the parameters following the same update rule. The delta thetas that we have computed according to the natural gradient update rule, and that's essentially the same procedure, but where I'm just preconditioning the gradients with the inverse of this geometric, with this metric tensor. Sorry. Yes.
Is the metric tensor just the numerical Hessian of the energy?
You can think it's very related to the Hessian. Yeah.
Well, just
it's
just in complex, I guess.
I mean, it's very much related to a second order method. Yeah.
Okay.
Yeah. And we can compare both optimizations. In blue, this is regular gradient descent. In orange is natural gradient. Issues of doing things live. Here, actually, natural gradient has gotten stuck.
I don't see it.
Oh, shit. Oh, that's okay. Okay.
Oh, maybe it's because you're sharing the.
Yeah, it's because
page
I
and
think
not
it's I'm sharing the Chrome page. Anyway, it's fine. It's in here. Well.
So, what's the intuition behind natural gradients? Is it like you are like allowing like a gradient, like a single gradient is just a first order approximation to its step down, and the natural gradient is like second order?
Somehow, but second order, the update in parameter space is informed by the overlaps of the wave functions. You want that once you update your parameters, the new wave function has an overlap close to 1 with the old wave function. That's the intuition. Is that I just don't want to like do a tiny step on parameter space.
Yeah.
Thinking of it as Euclidean distance. I want to give a step on parameter space such that my new wave function has almost an overlap of 1 with the old wave function. That's the main intuition behind it. That's how it was motivated by Sandor Sorella, essentially. Now, issues of doing things live, natural gradient. So sorry, blue is regular gradient descent, orange is natural gradient, which you see that has converged significantly quicker. Issues of doing things live, gotten somewhat stuck at the beginning, but seems like it's nonetheless worked. Now, I don't know if you remember from last Friday, but we explored a little bit what was the loss landscape of this model. So here, what I'm going to do, I just dumped all of the scripts that we used last Friday. So I can just call this function energy landscape, and it's going to generate the energy landscape for this model. Yes.
Before that, sorry.
Yeah.
So, but here, like it is a second order in the sense that you used only the second order of the Taylor expansion, and you could use more. Like, or is that wrong?
But I mean, it's second order in the sense that the metric tensor is somewhat related to the Hessian, right?
Oh, because I thought it was connected to the Taylor approximation. Expansion.
No. The Taylor expansion above you only do to first order, if I'm not mistaken. If I remember the algebra correctly, you only need to do it to first order.
Oh, okay.
And then the delta theta I, delta theta k appears because you're multiplying things. Okay. Again, here what I just did, I just dumped all of the code that I showed you last Friday to generate the energy landscape, but it's already done for us. So we can visualize what is the dynamics of both regular gradient descent and natural gradient descent in this energy landscape, essentially. Okay. White is regular gradient descent, which it's moving perpendicular to the equal energy surfaces. However, natural gradient has some completely different and very unintuitive exploration of parameter space, right? It's first giving a humongous jump to the right, which in parameter space is very far away. However, in wave function space, those two wave functions have an overlap of almost 1. So this natural gradient, this metric tensor that you've come up with, essentially is contracting and expanding this space of parameters such that things that before were far away now they might be close, and the optimization is much better. And again, as you are moving on each step, the actual wave function, the vector, is just rotating a little bit. This optimization procedure is much more stable rather than just like, I don't care about how this thing rotates when I update my parameters. I just care that the parameters are close according to the distance, the Euclidean distance, right? Which might perform a humongous jump, okay? So this is great. Again, we are going to run it. So this was one spin, which we know how to solve exactly, but let's actually run this on the model that we were solving the other day, which is this transfer field IC model. Again, defining the Hilbert space in netget. I'm defining the Hamiltonian using netget objects as well. I'm going to do exact diagonalization in this object to have a baseline, because this Hamiltonian is sufficient, this Hilbert space is sufficiently small, so I can just do exact diagonalization. But this is just to have a baseline, essentially. And while that runs, again, I'll show you that we are defining the model using flags. Again, where the model is essentially the exponential of a fully connected neural net with a single hidden layer, something extremely simple here. Then, again, I have to define the sampler, which the sampler, remember, is doing a Markov chain, and at each step it proposes to flip one of these spins, then accepts or rejects according to the ratio of the modulus square of the wave functions. Okay, I did not run that. Did it run? Okay. Okay, so, and again here, I'm going to store the initial parameters to start the optimization in precisely the same place with regular gradient descent and natural gradient. So we can compare both optimizations. Okay, so now we are using netget optimization drivers to just run regular gradient descent. Okay. So as we did last week. And I'm going to start showing you how easy it is to actually just tell the optimization driver in netget, okay, instead of just using regular gradient descent, just precondition my gradients, because in this space, people say that, oh, you're preconditioning the gradients by the inverse of the matrix tensor, right? So you just have to add to the optimization driver one input, which is the stochastic reconfiguration preconditioner, which is just computing this metric tensor that I've told you about. So great, so regular gradient descent has finished. Let's just run natural gradient. Any questions while this runs? Okay. Yes.
Okay, I have another conceptual question about natural gradients. So the goal is to do a gradient step and maintain the overlap.
Yes.
But I thought that was usually done with like the adjoint method.
What do you mean by the adjoint
So
method?
the adjoint method is like you do a gradient descent and then you project it onto the surface which conserves your constraint
Ah,
or something.
okay.
So is
I
the
see.
natural gradient just like a
I
better
see.
way to do it?
It,
something?
it is a better, I think it's a better way to do it. And also in our space, I would not be able to do the projection that you're talking about because to the projection, I'm living on an exponentially large Hilbert space. So I don't know how to project things by hand.
Okay, cool.
Yeah, yeah.
So I guess like the difficulty with natural gradients is you need to derive them for a specific problem.
Well, no, the natural gradients only depend on the specific wave function parameterization that you're using. So the neural net that you're using to define the wave function, and you only need derivatives.
But like if I want to use like natural gradients in like some astro problem, then I would need to derive it for this specific problem.
Yes, you would need to come up with a metric that makes sense for your specific problem. Yeah. Yeah.
Okay.
Yeah. Yes, yes. That's the thing. You need to come up with a metric that makes sense. So let's see how well both things did. This is regular gradient descent in blue, natural gradient, and as you can see, it converges much better. Oh, sorry. Doing the same thing.
Okay. You could just like share your full screen.
Yeah. Let me. Can you stop share for a second? Okay, let's see if now. No, it does. Really.
You can see it.
Oh, you can see it now? Okay, good. Okay, so regular gradient descent in blue, natural gradient in orange. Optimization is much smoother. Regular gradient descent hasn't even converged to the exact ground state, whereas natural gradient has indeed converged to the exact ground state. And I can also tell you very clearly that it has converged to the exact ground state, because so look at the fluctuations here. Okay, these fluctuations in regular gradient are essentially coming from the statistical sampling of the energy. Okay, but if you fall to an eigenstate of the Hamiltonian, the variance of your sampling becomes zero in the energy. So this is why you're seeing that essentially there's zero variance on the estimates of the energy. Yes.
So this is only when you're using a very simple neural network. But if you had something like a more complex neural network, this would be much more difficult.
Doing natural gradient, you mean? I mean, it is more.
You will need for every parameter, you will need the gradient by every other parameter, right?
I mean, the thing is that you always compute. I mean, it is more expensive. Yeah, it is more expensive, but it is more expensive in parameter space, which typically for us is not the bottleneck. The bottleneck for us is how big the vector space is. It's very rare the case where you have so many parameters in your model that this part of the algorithm becomes intractable. The issue is mostly when you're sampling. Sampling is what is our bottleneck. So if you just had, I don't know, instead of, I mean, this had 40 parameters, no, probably 60 parameters, if I'm not mistaken, or something along the lines. If you had a few thousand parameters, it's not a problem. Okay, so hopefully I've convinced you that natural gradient is a good idea. We've also done 45 minutes. I think we can take a break of 5 minutes if you want to go to the bathroom or just decompress a little bit. And then when we come back, we're going to start talking about fermions. So yeah, essentially at 2:23 or something, or 2:25.
think I've heard about natural gradients in the sense of likelihood functions and stuff like this.
Yeah, yeah.
There it would be the Fisher information.
Yeah, it's exactly efficient.
Yeah. So yeah, what I was thinking was like on act like neural networks or like or image recognition or stuff like this. You couldn't, right? You couldn't compute that actually.
Because probably those neural networks are
Yeah. But I mean, in this problem, you can.
And also in this problem, you cannot have humongous neural nets that take very long to evaluate because for sampling you need to evaluate the.
With the metropolis.
Yeah, exactly.
Do a lot of
evaluation, so it cannot take you forever to evaluate. Right? But yeah, it's essentially in the two works that this thing was derived simultaneously. The first one is in essentially
I think it comes from like Fisher.
Yeah, you're just matching two probability distributions, right? And then
yeah, so Fisher information where that is the geodesics on the parameter space.
Exactly. Yeah, and it's essentially the exact same idea. You're just changing the notion of distance. Yeah.
Have you seen these? I saw this paper that it's like they tried to derive all the optimizers in deep learning with natural gradients.
Isn't this? Oh no, I haven't
It's
seen
like,
that. Oh, that's interesting. Like all of the other ones are a particular case of natural gradient. Oh, that's so interesting.
All right. It's a really nice paper. It's called the
Bayesian learning.
And it's basically like every single algorithm, like atom, stochastic gradient descent, numbers, dropout, Newton's method, they're all natural gradients with a specific. The only difference is like what prior you have over parameters.
Okay, so that's probably the metrics that
Like,
you're using.
So it's like, yeah, you have this. You have a candidate distribution over your parameters, and you try to find like the best distribution. And then the Bayesian learning rule is like given an assumption for the candidate distribution. So like you assume any candidate distribution is like one part of the exponential family of the distribution. And then I think that's like it. I think you only need to make an assumption about the candidate distribution. And then that's like a natural gradient over expectation of loss minus entropy of the candidate distribution. And then basically what you can do, so it's like every single algorithm they say, yeah, normal stochastic or normal gradient descent is candidate distribution equals Gaussian. And then in Newton's method is candidate distribution equals Gaussian, but where you have an unknown precision matrix in your candidate distribution. And that's like the only difference. And then like regularized methods are it's like a different choice candidate. But like they have this is so cool. They have a chart of so that's like atom, even like dropout SGD. And so like this is what you use as your candidate distribution, and that's like what you use for the natural gradient. That's like atom, you approximate the natural gradient with like a diagonal. Yeah, you have like a diagonal, and then you have slow moving scale vectors, and that's like technically an approximation of the natural gradient or something. Yeah.
That's
but it seems like they're deep.
Point of view.
So natural gradients are so cool, but I still don't understand.
Oh yeah. I mean, I understand the intuition that this is a very particular problem, but in general,
Wait, is that yours? Stochastic variation. No, which one?
well, I mean, ours. I mean,
Oh, is this
I would need to take a very careful look at it because the distance, I mean, our probability distributions are not definite. I mean, they're definitely positive, but you're moving on the space of 4 laps outside. Probably it's fine.
Okay, yeah, I guess I knew that.
Yeah. That'd be great.
Yeah, I'm still, okay, I've read this paper like 5 times, but I don't understand it. It's so very
Yeah.
And the guy who wrote it, he posted on Twitter, like, I spent like 5 years writing this paper.
Wow. Okay.
Yeah, I just read it this year. No, he's just saying. You're in. That's not what I don't know how to do it. How is this something?
Oh no.
But it's also, I think I'm too old. When I was younger, I would get like 2 all-nighters in a row. Right, anything is like a all-nighter. Too old now. I can't do it anymore. Like I tried to stay up all night and I'm just yeah, I mean, I think I was a little crazy for trying it. But at least I got rolling.
Yeah, that's good.
And I spent way too long.
You can write more.
On the wall.
Yeah.
I literally.
I don't know what I'm not with that.
It is
Now it's also.
colors. One later. Letter. It's green and blue.
Okay, I think we are probably going to continue now. Okay, so now we're going to apply everything we've learned to actually a little bit more of an interesting problem. And well, in the past couple of years, I've been thinking a lot about fermions and how to generalize this type of ideas of using neural nets to parameterize quantum states, but now the quantum states represent fermions. In this context, we're going to be thinking on a lattice with L sites, and we have N fermions, which for our purposes are going to be electrons that can hop between the sides of that lattice. But okay, the notion of fermion or boson comes from the notion of particles being indistinguishable from each other, right? Doesn't matter if I exchange the label of 2 particles, the physics of the problem should be the same. In the case that we did before of spins, that was not the case. Each spin was localized in space in my 1-dimensional lattice, okay? So I could say this is a spin number 1, this other one next to it is a spin number 2. So there's no notion of indistinguishability because I can label them. Now, if I have 2 identical particles hopping in a lattice, I cannot label them. I don't know which one is electron 1 and I don't know which one is electron 2. There's nothing that distinguishes them if they're hopping around. So, okay. Now, the other thing that it's important, I'm going to be changing a little bit the notation now. the quantum states before, I was calling them sigma, and they were like +1, -1, -1, +1. And I have particles hopping on a lattice. So the quantum labels are going to be here x, which is just a vector of positions, x1, x2, up to xn, position of particle 1, position of particle 2, up to position of particle n. Okay? Now it seems like I'm cheating a little bit because I'm adding labels to the particles, but we're going to see that we're going to by hand impose that things do not depend on these artificial labels that I'm adding here. Okay, now we're going to, and wave functions now acting on this n particle space are going to be these functions psi of x, which depend on these vectors of coordinates of positions. Now, let's see what happens if I act on these wave functions with the operator that swaps the labels of two particles, right? So this is what I'm calling Pij. Pij just swaps the indices of particles I and j, right? So Pij acting on the wave function psi of x, which has labels x1, x2, xi, xj, blah, blah, all the way to xn, returns x1, x2, xj, xi, okay? Just swap I and j, nothing too relevant, right? But we realize that if we exchange particle labels twice, so if you apply the Pij, twice Pij to something that you have already applied Pij, right? So if I apply Pij once, I end up with x1, x2, xj, xi, but if I swap them again, I end up with the same thing, right? x1, x2, xi, xj, xn. So this is this thing that I'm saying, let me make this bigger. This thing that I'm saying is completely trivial, right? Just that if I change the label of particles twice, I end up on the same quantum state. That means that this exchange operator that changes the labels of two particles, the square of that operator is the identity. And if the square of that operator is the identity, that immediately leads us to conclude that the eigenvalues of that operator can be +1 or -1, okay? And also we know that the wave functions of indistinguishable particles have to be eigenfunctions of this exchange operator, right? Because I don't want the wave function itself to change if I apply the exchange operator because my particles are indistinguishable, okay? So that means that Pij psi has to be the eigenvalue psi, okay? But I've said that there's two eigenvalues, +1 and -1. The types of particles that have +1 eigenvalue is what we call bosons, okay? That means that if I exchange I with j, the wave function is exactly the same. Psi x1, x2, xi, xj, okay? Nothing has changed. So wave functions are symmetric with respect to exchanges of the indices of these input vectors. Now fermions have a -1 eigenvalue, okay, on this exchange operator. That means that psi x1, x2, xj, xi has to be equal to minus psi x1, x2, xi, xj, okay? So if I change the label of two particles, the sign of the wave function has to change, okay? So the wave function has to be antisymmetric with respect to particle label exchanges. This has very profound implications. Like for example, there's no two particles that can be in the exact same position or in the exact same quantum state because the wave function of that thing would just simply be 0, right? If they are in the same position and psi of two particles, so if they are in the same position, and I have x1, x2 equals minus of psi x2, x1. But if I say x1 equals to x2 equals to x, that automatically implies that psi of x equals to minus psi of x, which implies that equals to 0, right? So that means that I cannot have two particles on the same position, and in the very same way, I cannot have two particles in the same state. When I'm doing chemistry, as we're going to start doing now, and we'll start filling up, like in your high school chemistry classes, when they ask you for the electronic configuration of a given atom, and you had 1s, 2s, 2p, and they told you, okay, you have to start filling from the bottom to the top, but you cannot repeat particle labels. This is coming from the fact that the wave function is antisymmetric. So, for example, if helium was 1 electron up, 1 electron down, right? But I couldn't put something like 2 electrons up in the 1s, because that's the same quantum state, and that would lead to the corresponding wave function to be 0, right? So that state is not allowed. Great. So there's an experimental module with, yes.
So the question, sorry, the reason why it can't be 0 is also because it's like an eigenstate of.
Yeah, it's also I mean, it's also an eigenstate of the exchange operator.
Okay,
right?
so that is the fundamental reason why it can't be 0. Why psi cannot be equal to 0 anyway.
What do you mean that psi?
You said that if you assume it to be antisymmetric, you get psi of x comma x equal to 0, right? So they can't.
Yeah, I mean, you cannot. Yeah.
But my question is, why can't psi be 0? Is because
no,
it's an eigenstate.
No, psi can be 0. Like, in fact, when you are dealing with fermions, well, I mean, psi of, let's say, if it has two coordinates, two particles x1, x2, this object can be 0. Even this can be 0, even if x1 is not x2. Yeah, this object can be 0, indeed. But that is not in tension with the fact that this object is antisymmetric. That just means that psi of x1, x2, which is equal to minus psi of x2, x1 for a particular x1 prime, x2 prime, this can be 0. There's no fundamental limitation to that.
I see. So what you're saying is that the probability that we observe such a state is effectively 0. Right?
Yeah.
Okay.
I mean that happens sometimes, but not necessarily because x1 prime equals to x2 prime. If x1 prime equals to x2 prime, then yes, this is automatically 0. That's for sure. But there's other regions in the wave function space where this thing is also true. Okay. And one example of something like that is, let's say, the wave function of an electron in a hydrogen atom, for example. Well, this is the atomic nucleus, the first, the one with the lowest energy. If you just take a cut along one of the X, Y, or Z, this thing is something, well, actually, is a little bit ill-defined. Like in the middle, you cannot have electrons, right? And also at infinity, you essentially don't have electrons, because otherwise also the probability distribution that is defined by the wave function is not normalized. Right? So there's regions of position space where the wave function is in this 0, right? And it is 0 in the nucleus because Coulomb repulsion, right? The repulsion is so strong it doesn't want to be there. It's also when you're doing things in spherical coordinates, things get messy with the origin. But anyway, okay. So what I was saying is that Netget has an experimental module to dealing with fermions. Well, effectively, all of these signs are swept under the rug into the operators when you're applying operators, but we're going to do things explicitly where we want to add the signs into the wave function. So what we are going to be simulating now is what we call the Hubbard model in one dimension. So we are going to consider a lattice that has L sides, which L equals to 8 and is in one dimension. But it's well, it's actually the Hubbard model. We're going to think of the Hubbard model as being two lattices. Okay, so imagine a one-dimensional lattice. Okay, and then we're going to put another one-dimensional lattice right below it. Okay, what I'm calling L here. So this is 5 sides. L is equal to 5. Okay, but there's two lattices on top of each other. And there's two types of electron species, one that live on the up lattice and one that live on the down lattice, okay? And I'm going to be labeling them as up and down. I'm saying this because this is going to appear in the definitions that I'm going to be using. Yes?
So these are one-dimensional lattices.
One-dimensional lattice.
With 4 or here is 5-dimensional.
Well, periodic boundary conditions. Okay. So, fine. But yeah, there are two rings, one on top of the other if you want. Okay. But yeah, this is to not make the drawing messy again. That one. But anyway, so n up, that's the number of electrons that are going to be living in the up lattice, and down, the number of electrons in the down lattice. So we have 4 and 4, and well, and here the lattice has 8 sides instead of 5, right? So Netget also has a module to create graphs. In particular, here we are going to create a cube in one dimension, which is a ring with periodic boundary conditions of the given length that I'm interested in, so length 8. So we can ask this object, okay, how many nodes are there in this graph? So there's 8 nodes, 1 per lattice site if you want. And what are the edges of the graph? So the connections between sites, right? So 0 is connected to 1, and also 0 is connected to 7. This is the periodic boundary conditions. But then 1 is connected to 2, 3 to 4, 2 to 3, and so on. So here you're just specifying all of the connections that define your one-dimensional lattice. Now, we're going to be thinking a little bit about fermionic operators and what type of operators we are interested in. The first one, well, and also in this lattice, so there's electrons and they can hop between adjacent sites, but on their own respective lattice. We do not allow this type of hop. Okay. That's not allowed. They only hop in between their own sites. Now, the operators that we're going to be interested in these types of problems, well, the first one is the creation operator on a given lattice site. The creation operator, if the site is empty, here represented by a 0, it just adds 1 particle to that site. Okay. So if this given site is empty and I act with the creation operator on that site, puts a particle here. Okay. But if that site is already occupied, remember, there's not 2 electrons on the same site. If that site is already occupied, it returns a 0. Okay. Due to Pauli's exclusion principle. Then we also have annihilation operators, which are the complex conjugate of the creation one, but they have the opposite action. If there is a particle on a given lattice site, and I act with the annihilation operator, I just remove it. But if there's no particles, then just return 0. And then the last operator that we are interested in is the number operator, okay, which is just this particular combination of creation and annihilation. This is, if there's a particle on that given site, I remove it, and then I add it again. So essentially, it does nothing to my basis states, but it counts the number of particles. So if there's 1 particle, it returns the exact same state. But if there's 0 particles and I try to remove a particle, it's going to return 0, which is the number of particles that you have in that site. So now again, Netget has its own module for these types of operators, which are fermion create, fermion destroy, and fermion number. Okay, and I'm just defining here some functions to access them a little bit easier, because they take the Hilbert space that they are acting on, they take the site that they are acting on, but then this SC label, this only is telling me in which of these sublattices they're acting on. So if up is represented by SC equals to +1/2, and down is represented by SC equals to -1/2. Okay. Why are we using this very particular labeling for up and down lattices? Is at the end of the day, this actually represents the spin degree of freedom of the electrons, but that's just some technical details. We can just think about these things as two separated lattices. Okay, so we define those functions to create C dagger, and the number operator, and the particular Hamiltonian that we are going to consider, yes.
You said the electrons can't jump between.
They cannot jump between up and down lattices, no.
Then why do we consider both of these things at once? Like, why can't we?
Yes. It's because they do interact with each other, but they don't jump.
Okay.
The Hamiltonian, which is written here, actually has, this is a hopping term, okay? This tells me, oh, okay, this is, oh my God, it has a horrible typo. This shouldn't be dagger, okay? This shouldn't be dagger. That's okay, fine.
Superconducting.
Yeah, so suddenly superconducting. Well, it's fine, I'm gonna get lost and then I'm going to, anyway. Imagine that this is C and not C dagger, okay? This removes a particle from site I+1 and adds it to site I. So this first operator is doing this jump, okay? And I have the complex conjugate of that operator. Again, this doesn't have a dagger. So this removes an electron from site I and adds it on site I+1. So it's doing this other jump, okay? So both jumps to the right and to the left. The same operators on the down lattice. And now we have a term that is interactions. This is repulsive interactions between electrons on the lattice. If I have two electrons aligned, this is going to cost energy. This doesn't cost energy between these two, but the energy cost, here the energy cost is quantified by U. But this indeed costs energy. Now, you can think of this model and also why it describes metals, so things that conduct electrons and things that don't conduct electrons. Imagine removing this term here, okay? This Hamiltonian is telling me I want things to jump around. This is a conductor, okay? Electrons are moving around. Now, if I add this term here and I make it to be very large, now particles are going to, they don't want to be aligned. So if I have a particle here and a particle here, what is going to go down in the down lattice is that I'm going to have the opposite one here, one here, one here. This term causes particles to localize. Okay, so this is a transition into an insulating state, but the transition is driven by the interactions amongst electrons, which is something very uncommon. In solid state, typically you learn about insulators, but they're driven by interactions with the lattice potential and so on. But this is something a little bit more fancy. Yeah.
So is this a modeling decision to say that the diagonals?
These guys don't interact with each other.
But that's like a modeling decision, or is that?
That's a modeling decision, yeah. Yeah. You can include these types of interactions as well.
Is that something that is done?
In 1D, yeah. In 2D, 3D, Yeah,
non-local.
yeah, but yeah, in real materials, of course, that is not the case, right? Things have longer range interactions, but this too good approximation is not horrible. But
from electrostatic. So this is just the interaction between two electrons. It's full of interaction with static electromagnetism. And this is infinitely long range.
Oh, so you would want, if you have a lattice, more dimensions, you would want it every electron.
The other electrons are now screening this long range. So the material in general don't have very, very long range. The interaction is not infinitely range, but still.
yeah, this is the model of electrons that are very tightly binded to their atoms in a solid. Okay, so this would be this big dot here would be the lattice site that I'm putting, and these are the electrons, but they are very tightly binded. But they're allowed to hop between according to this term T. And what Domenico is saying, okay, the way the electrons interact is that, well, the Coulomb repulsion has a very long tail, right? So this one is going to see the presence of this and this, but for our purposes, we're just going to say, okay, zero. We don't care. We only see interactions if there's two electrons that are attached to the same atom, essentially. So you see it's a very big simplification, but it's complicated enough so people don't know how to solve this model. Yes?
Oh, could you repeat which ones didn't have the
Oh, I'm sorry. This doesn't have this. This doesn't have the ones, the second ones. Sorry. I can give you an updated version as well. Okay. So now I created this Hamiltonian using Netcat, and I can ask it to produce what are the terms. Here it labels C and C dagger and the site that they act on by just telling me which site they're acting on, and if it has the raised to the power symbol, that means that that's a dagger, and if it doesn't, that means that that's not a dagger. So anyway, we can do exact diagonalization to have, so I only have 10 more minutes, so I'm going to have to speed up a little bit to have the energies. And then for sampling, what I'm doing here is I'm defining the two disconnected lattices. So then the sampler is going to propose jumps of particles. Okay. Now, antisymmetric wave functions. How do we construct antisymmetric wave functions, right? I can brute force my way through computed antisymmetric wave functions. So giving an arbitrary function here, what I can just do is, okay, sum over all possible permutations of particle levels and multiply by the sign of the permutation. Okay, so that produces an antisymmetric function. But there's n factorial of these permutations, right? So if I'm trying to solve a problem that scales exponentially in the number of particles, and it costs me n factorial to evaluate amplitudes, doesn't make any sense, right? So completely discarded. You can think, okay, fine. What if this function here has a very precise structure? What if it's the product of functions that only take a single coordinate? Okay, sure. I mean, I can plug it on the same formula, and well, very quickly again, this has n factorial terms, but I realize this actually is a determinant. This is the formula of a determinant, right? So this thing I can write as a determinant where I have n of these phi functions, so phi1, phi2, all the way to phi n. And the matrix that enters the determinant is, I just take phi1, put it in a column, and evaluate it in x1, x2, all the way down to xn, phi2, x1, x2, all the way down to xn, and so on. And this is how I evaluate my determinant. It's changing particle labels now. It's changing rows in the determinant, thus change of sign, which is what I want. But I mean, I hadn't found too profoundly about it in my undergrad classes when they taught us these numerical techniques to compute determinants. But what you see, if you try to brute force a determinant, it has n factorial terms. So you wouldn't be able to evaluate it. But luckily, the determinant is invariant under changes of basis. So it can rotate the basis in which this matrix is represented to have it like upper triangular or lower triangular, and then the determinant is just the product of the diagonal elements, and basis rotations are just polynomial in n here. So determinants can be evaluated in polynomial time, even though if you try to brute force it, it's n factorial, which is a very fun fact. But determinants don't carry out entanglement. So they are not going to be able to describe these interactions very well, actually, or they're going to do a very poor job. So we want improvements over determinants. Yes.
It's because it's the factorization to the product of singular products. Is that why you can't, like, the determinant isn't good enough?
Yeah. It's because what he's asking is that in many body wave function states, there's a particular class of wave functions which are just products of the local Hilbert spaces functions. This by definition doesn't carry out any entanglement, and this does not describe well systems of interacting particles. The determinant is the generalization of that thing to indistinguishable particles. To have something a little bit fancier, I can multiply the determinant, which is antisymmetric, by a symmetric function, okay, of the particle positions. A symmetric function without loss of generality can be a function of occupations in the lattice, right? Zeros and ones. If I exchange two particles, the zeros and ones associated do not change. And that I can represent by a neural net. So there are some works that have explored this idea. Another option is backflow transformations, which is now in my determinant, instead of having single coordinate functions phi1 to phi n, what I'm going to do is allow them to depend on x1, but also on the occupations on the rest of the sides. Now they have information about the position of the rest of the particles, and this carries out entanglement as well. This is what the people from DeepMind did on their paper, essentially. This Fermi net, if you see it around, is a backflow in that sense. Yes, essentially that's okay. That's pretty much everything that I wanted to tell you about antisymmetric wave functions. We're going to do one. Well, okay, I have very little time, so instead of actually solving the Hubbard model, I think it's more fun if we solve the dissociation curve of H2. And the particular wave function ansatz that we're going to use is a determinant multiplied by a neural network of the lattice occupations. And in H2, you might see, okay, fine. We've talked about lattice model, how the hell is that connected to a molecule? Well, a molecule in the 1s, 2s, 2p orbital representation, we can think of as a lattice that is occupied by fermions hopping around. This is actually how quantum chemists solve molecules when they do Hartree-Fock, coupled cluster, or different methods. This is what we are going to do. Okay. Right. Maybe I should have followed the order of the tutorial, because now I don't have imported the libraries that I needed to import. Anyway, again, small molecules, we're going to write very similarly to the Hubbard model, how we wrote it, but a little bit more complicated in the terms that it contains. Those terms we just obtain from ISEF, and one of the scripts that I passed you has a couple of functions to ask for those pi-SCF coefficients and then turn them into a Hamiltonian that Netcat can understand. pi-SCF also does exact diagonalization for you. So this is the energy of the molecule. So we are going to compute the H2 molecule for different distances. And this is what is going on right now. It's computing the first distance where the two H atoms are very close to each other. Yes.
Just a general question. Is there any way to get around evaluating in terms of coefficients when you're doing this kind of things?
Wait, is there any way to what? Sorry?
Is there any way of like avoiding the evaluation of port matrix when you're doing these methods? So for integrals, this is what leads to that.
Oh, the integrals, you mean? No, you have to obtain the integrals.
Yeah, to obtain them.
Yeah. But that is easy to do. You can just call pi-SCF. Ask pi-SCF to do the integrals because pi-SCF is computing integrals of this type of object. And then this 1s, 2s to be at hydrogen-like orbitals for you.
So you're basically bound to the complexity class of the starting point. Is that correct? Or
why do you mean? What do you mean by bound by the complexity?
I mean, empty power free. If you have these tightly available for integrals.
Well, the electron integrals don't depend on Hartree-Fock.
Okay.
The electron integrals are independent of Hartree-Fock.
Of course, yes.
Yes, but why do you mean that you're bounded by Hartree-Fock?
I'm just wondering whether how this compares complexity-wise to other wave function-based.
Oh, okay, I see. The asymptotic scaling is the same as Hartree-Fock and then multiplied by a prefactor.
Okay.
Yeah,
I see.
Yeah, Hartree-Fock. What he's asking is Hartree-Fock is just considering a Slater determinant. The complexity of evaluating a determinant goes as the number of particles cubed, essentially, between 2 and 3, depending on how serious the determinant is. We need to compute a determinant and then multiply it by a neural net. So cubed on the determinant and then in the valuation of the neural net is typically squared, I guess, depending on what type of neural net you are trying to evaluate. This is regular affine transformations.
Okay, so the determinant is kind of the trickiest part.
The determinant is always the trickiest part, yeah. And also, as a technical note, implementing the determinant in JAX is a little bit messy because JAX hates doing in-place updates. And the way that things are done is you have to, the way that you construct the matrix for the determinant is by slicing another matrix and then put it in one matrix. So this slicing and putting into a matrix, JAX does not like. But anyway, I think we've computed the dissociation curve of H2. I'm sorry I was not able to go over any details on this part at all, but this dotted line is a single Slater determinant that does not capture entanglement. It's so bad that, this is the distance between the two molecules, okay? And this is the energy as a function of the distance of the two molecules, right? So the stable configuration is here the minimum. When they are very far away, the energy of this thing should be the energy of one hydrogen atom plus the energy of the other hydrogen atom. Single Slater determinant does not capture that. It tells you that the energy is higher than the sum of the two energies, so it's crap, essentially. That is what is called size consistency. Now, the very thick black line here is the exact diagonalization result because H2 is a very small molecule in the basis that I was using, so the number of degrees of freedom is very small. And now this blue dots is the Slater, so the Slater determinant multiplied by a symmetric neural network on the configurations of particles, which essentially has exact agreement with the exact solution.
Slater determinant is what we saw before, right?
Yeah, Slater determinant is is the determinant.
Yeah.
Okay, sorry, yeah.
So every blue dot is a different neural network, or is it?
It's a different neural network. So for every blue dot, you have a different Hamiltonian, and you have to re-optimize the wave function from
So
scratch.
for every distance, you need a
Yeah, for every distance, the Hamiltonian changes, and therefore you have to restart the optimization. Yes.
One way you have to start was like when you're in kind of an adiabatic limit, can you just kind of
You can recycle.
just a little bit from an old starting point, or
You could recycle, but that's dangerous if there's phase transitions.
oh, okay.
Yeah, recycling is typically a good idea. You can recycle the parameters. So if you've computed when they are very close together, the ground state, you can recycle those weights and then start the optimization from there. But the issue is that if there's a big change between two of the Hamiltonians that you obtain, you may get stuck in a local minimum, for example. But yeah, I mean, typically, yes, you can recycle parameters.
After actually.
Yeah. Maybe.
Okay. So thanks everyone for coming to Mitya's talk. We think so. There's some new students, so we were thinking we could go around and just everybody introduce themselves and say like what center you are working in. So I can start. So my name is Miles Cranmer. I am from Princeton, but I spend a lot of time at the CCA. I work with Shirley Ho and David Spergel. Okay, want to start?
Sure. I'm Lindsay Kwok. I am a student at Rutgers University in New Jersey, and I'm working at the CCA with Miles and Shirley this summer.
My name is Masima. I'm from the University of the Western Cape in South Africa. I'll be with the CCA. I can't pronounce the name of my mentor, and I apologize to them in advance.
Thanks. Yeah.
Hi, I'm Roy Friedman. I'm from the Hebrew University in Israel, and I'm going to be working with Sultan and Shule in the CCA. I'm Andrew Heralde. I'm a fourth-year PhD student. I'm working with Sian Chung on representations and manifolds.
I'm Matthias Müller from University of Vienna, and I work at the CCQ with Domenico for dynamics in electronic structures.
My name is Leo Epstein. I'm a student at Humboldt University Berlin, and I'm working with Barbara Engelhardt, heart-to life cell emitter.
Hi, my name is Akihiro Yamaguchi from NYU. I work with Alex Williams at CCN.
Okay, hi, I'm Elena. I'm from Munich University. I'm working at CCA with Miles and Shirley.
Hi, I'm Thomas. I'm also a PhD student at the University of Munich, and I'm also working with Miles and Shirley at CCA.
Hi, I'm Michael Hatzanastasis from École Polytechnique in Paris, and I will work with Frank Zhang in graph neural networks for cancer prediction.
Hi, I'm David. I'm from the University of Amsterdam, and I'm working at the CCA with Kees Wong and Shirley Ho.
I'm Natalie Sauerwald, and I am a postdoc at the Flatiron and CCB.
I'm Mita Shklovsky. I'm a group leader here at the Center for Computational Neuroscience. The group is called Neural Circuits and Algorithms.
Okay, thanks everyone. Yeah, please welcome Mitya. Very excited for his talk. Thanks.
Thanks for inviting me. So I want to start from a very simple observation that everyone is talking about neural networks, but there are actually two completely different things that have this name. One is the artificial neural networks, and the other one the biological ones. And it is true that when neural networks were invented, their creators drew inspiration from biology. But that was more than 60 years ago. And since then, the two fields kind of divorced and went their own separate ways. the development of the artificial neural networks basically followed engineering improvements and try to move in the direction of better performance, obviously, without drawing much more inspiration from biology. And at the same time, we know now much more about what neurons do and how they connect and so on, that it doesn't look like what the real biological neurons do can be captured by the deep convolutional network, for example. So let me get a little bit more specific about this. So first of all, as you know, this deep convolutional networks operate in a supervised setting, and they require large labor data sets to train and to perform well. And, of course, there are GANs and there are all kinds of things, but they're built on top of this supervised trained networks. Okay. In biology, it's the other way around. Okay. The neurons are mostly acting in an unsupervised fashion because typically there are no big label data sets. And whenever labels are available, it's rare. And then few labels are usually enough for you to learn new things, right? If someone tells you, okay, that's a new animal, you can next time recognize that animal, even if it doesn't look exactly the same. Of course, this is not always the case. There are cases of learning instructions in the brain, and we'll get to that, but we will start with unsupervised learning. A very important difference is what kind of learning rules are allowed in biology, and those learning rules have to be local. What do I mean by that? If you have a synapse that connects two neurons, I and J, and Wij is the weight of that synapse, the update of the synaptic weight can depend on the activity of only the two neurons in the whole brain. The two neurons that synapse connects. Why? Well, because it's just physically impossible for that little synapse that is embedded in the jungle of neuropil to get information about other neurons' activity in any kind of specific way. Of course, you can have some average activity or total activity available to the synapse, average for a large population of neurons, like 1,000 or 100 of them, but you cannot have specific individual activity of neurons other than the two that the synapse connects. Okay, so that's why the learning rule has to have this. Of course, this is not the case for error back propagation, because as you know, you have to compute the error in the last layer, and then you have to ship that error upstream in this network, multiplied by the synaptic weights of the forward pass along the way. Okay, there are all kinds of tricks to try to implement this in networks, and we'll talk a little bit about that. But by and large, this is just not going to happen in the brain. And also an additional problem is that, if you ship the errors backwards, you can have like a shadow network that just propagates errors. That would predict that in the brain, you would have like value neurons and error neurons. That isn't really the case. Okay, so that's another knock on this analogy. And there is another observation that I want to make is that that the units in artificial neural networks, they perform weighted summation followed by rectification, usually linear units. But biological neurons are not like that. Yes, from maybe in the 60s you could have said that, but now we know that neurons have very interesting temporal dynamics. They have compartmentalized computations where parts of neurons sum the incoming signals and then process them non-linearly. So none of that is reflected in those simple units. Please.
Do you feel like that maybe if you abstract neurons to just neurons and synapses, the things on the right hold, but maybe like within each neuron, there are more complex computations that could be happening with like ion channels and neurotransmitters and things like that along the synapse, let's say, or something.
Yeah. So there is a lot more computational complexity in neurons. That's what I'm trying to say, if I understand you correctly. Right? It's not just a ReLU unit.
In the brain, how many connections can one neuron have with other neurons? Like how many synapses?
So that's a really good question. So the average in your brain is probably between 1,000 to 10,000. So it's thousands of incoming neurons and thousands of outgoing. Okay, there is one structure where a neuron can get 1 million synapses in. Wow. Okay, so that's clearly something very powerful about the brain, and certainly way beyond what existing semiconductor chip electronics architectures can do. So they're very limited. They call it fan in and fan out, and they're limited. It cannot be more than 10, basically. In most circuits, the reason is because you have to. It's all electrical, and so you have to, the voltage leaks out if you have very big fan out. The reason neurons can do that is because all those signals propagate electrically along neurons. To cross from one neuron to the next in the synapse, that's a chemical transmission. So it's very high output resistance, meaning that if I add a few more synapses in the output, it's not going to drop my voltage in a neuron because you just signal chemically. There is no current leaking out. That's a very, very important difference. And when I talk to, electrical engineers who design electronic chips, they're all like, wish they had something like that. Any other questions? All right. Well, whenever you have a question, don't hesitate to interrupt me. That's the point of the school. So these are major differences, and it's important to be aware of that. But I wanted to be fair, okay? Those things are not completely different. Okay, there are some similarities. Okay, so just to be fair. Okay, so if the brain doesn't use error back propagation as its workhorse, what does it use? What are the mathematical algorithms that neurons actually implement? And that's the goal of my research. And to answer this question, I think it's best to go back to the basics that I'm sure you all covered here. So I go through this quickly, but still, okay? So why is learning in high dimensional spaces a difficult problem? Well, that's because of the curse of dimensionality, right? So if you go from 1 dimension to 2 dimension to 3-dimensional space, and you want to be able to classify examples that can occur anywhere in this space, shown here by these cubes, you need to have training examples from each of those cubes, right? So then you will know how to classify examples from the test set that will come later. But the number of those cubes grows exponentially, of course, as n to the d we're here and it's 5 and D keeps growing. So for a problem of interest, say vision, there are about 1 million fibers, 1 million axons that go from your eye to the rest of your brain. So this is basically a 1 million dimensional space. And you have to solve a problem of like face recognition or something like that. That's, of course, where cursive dimensionality will come in. Okay, so how can learning work at all? Of course, you know, there are theorems that, theorem that tells you that, okay, in the generic distribution, such high dimensional space, it's exponentially expensive to learn. But what if the distribution of data was not uniformly random and there was some special structure? For example, there could be a low dimensional subspace where the data sits. And if you knew about that subspace, you could index those points in a lower dimensional space and classify, for example, very straightforward. Of course, subspace is just a linear manifold. The structure doesn't have to be linear. There could be a nonlinear manifold. Yet, if there is some dimensionality reduction like this, it will allow you to reduce the amount of data that you need to learn the manifold and then to train your algorithm. Okay? So what we're going to do is to go over algorithms that can discover this latent structures in biological way, starting with unsupervised and then slowly fill them in supervision. Please.
So in images, I can understand what a single data point is, but if we're talking about vision, like human vision, then when I see a person's face, what is a data point here? It's like I see a continuous time version of the person, and like this is clearly more, or I don't know, this is not the same amount of data as there is in one image from computer vision, if that makes sense.
So yeah, so for vision, the way I think about this is, you know, it's a space of pixel intensities. So if you have 1 million pixels, right, this is a 1 million dimensional space, and each specific image of the face is a point in that space. Okay. Now, you of course can identify that face when it changes its pose or illumination, or, you know, they shave their beard. So of course it's not a single point, and I'm jumping ahead here, but since you asked, right? One way to think about this is that, you know, images of the same face, you know, lie on this high manifold that is embedded in the high dimensional space. So again, this is the space of pixel intensities. And then if the person turns their head, you kind of traverse that, say, blue manifold. Okay? Does that answer the question?
Well, kind of. I asked because you talked about learning complexity, like data complexity that you need to learn the space. And when it's in the images, I understand, like, I understand what is a data point, but actually when it's a human watching something, I don't understand what is a single unit of complexity, like of data point. If that makes sense. I understand what you mean. I do understand what you mean with the manifold, but just
well, think of it as you know, receiving video frames.
Okay.
So you're receiving frame after frame, still frame after still frame, and they change a little bit from frame to frame, but each of the frames can be viewed as a vector in this high dimensional space. Does that work?
Yeah.
Okay. All right. Okay. So I will start. So to learn this lighted structures, I will start with the traditional so-called reconstruction and decoding approach, which is an example of which is autoencoder that you know about. And we'll start by showing that a single neuron can actually find a linear subspace by basically performing principal component analysis. And then we'll try to generalize this to multiple neurons, and we will run into trouble. And that's where I will introduce a more recent singularity matching approach that we developed that solves this difficulty, but then allows you to not just solve the linear manifolds, but also the nonlinear ones, and eventually to go over to the supervised set. All right. So principal component analysis, you probably covered it in this course, right? So this is, for example, a two-dimensional input space. You have a data, which can be represented as a vector, as two components, x1 and x2. But there isn't just one data point, there is a whole cloud of data points. And the goal is to compress that data set by projecting it onto a single direction we'll call W that may, they usually say for PCA, maximize the variance of the projected data, or equivalently, and that will be more convenient for us, minimizes the reconstruction. So these two definitions are actually equivalent, and you can do a homework problem showing algebraically that they're the same thing. But if we start from this, it's just more convenient. So for each data point xt, we want to find a projection yt, which is a scalar here, onto a vector w that reconstructs that data point where the error is given by that mismatch shown here in blue. And we want to minimize that mismatch squared, averaged over all the data points from 1 to capital T. We keep the norm W fixed. Okay. So does anyone know how to solve this problem? What is W given by in terms of X?
The eigenvector of the covariance.
Excellent. Thank you. The W is the eigenvector of the covariance matrix, which corresponds to the highest eigenvalue. Okay. So if you do that, then it kind of lines up with this direction, and that minimizes the average reconstruction. So this is PCA in the offline setting, as a old school statistician would do. They would load the data on the computer and run the eigendecomposition of the covariance matrix to find W, and then compute the projection of St onto W, and that will give you the result. But a neuron doesn't have that luxury because it doesn't have access to this, big memory unit, and it never gets the whole data set at once because, the neuron is sitting in your brain and it gets streamed data from your sensory organs like your eye, okay? And it has to produce output on the fly in real time. And it can't wait for receiving the whole data set because by that time, you're dead. So you have to do this in the online setting. And it's actually non-trivial that such algorithm indeed exists. And it was invented 40 years ago by Finnish scientist Oja. Basically, the idea is that each time point t, you want to find yt, which minimizes the reconstruction error while you're keeping w fixed. Okay, so you assume you have some okay w estimate from the previous time point, t minus 1, and you find y that minimizes the reconstruction. I kind of already gave away the answer, but there is a couple of algebraic steps that prove that the y that minimizes this reconstruction error is simply the projection of x onto w. Okay, so just complete the square and then take w. Yeah, you expand this and then complete the square in terms of y alone. Okay, so you can just move w from here to there. All right. So y is just a projection of x onto w, and that's of course what you see here. And that's great. Why is this great? Because that's what neurons can do. Right? The first thing you learn about the neuron is that it can receive a vector x, where each element of the vector is an activity of an upstream neuron, x1, x2, and so on. And then activity of these neurons passes through a synapse whose weight is W1, W2, and so on. And then the neuron sums the weighted inputs that come from upstream. So basically, that's what the neuron does. It performs weighted projection of the input data that is streamed to it by, say, the sensory organs. Okay, so this is how you can compute y for every incoming vector x, but we are not done yet because I told you, well, you get w from the previous time step, but how did you get w at the previous time step, right? You have to learn it. And that's kind of the key, sort of the meaty part of any algorithm is the learning rule. And Oja came up with one. And Oja's learning rule is shown here. You can obtain it by just taking a derivative of this objective function with respect to w for a particular time point. So you take just one term here, like this, and then you differentiate with respect to w, and you get this thing. Okay. Yes.
Are there experiments people have thought of to actually like test out the Oja neuron and see if like isolate a neuron or something and like give it inputs? Is there a way to test it?
So yes and no. If you look at this learning rule, it has two terms. The first cross term is the product of the activity output of the neuron yt and the input, corresponding component x1, x, and so on. And so that is so-called Hebbian learning rule, and that actually comes from physiology. Yes, neurons that fire together wire together. So that is known. But that's not the whole story. If this happened, the only thing that happened that the synaptic weight would go up without a limit. So something has to constrain it. And in this case, it's a term which is wy squared. There are other learning rules with other constraints. Now, what the right constraint is, we don't really know. We also don't know if this exact form is the right form because there are also other effects that I don't want to go in. So as usual in biology, we can say that roughly it makes sense. but we cannot say it's exactly right or it's exactly wrong. So it's in the right ballpark. But if you use that learning rule, of course, and you run this algorithm in an online setting by throwing data vectors and adjusting W according to this and keeping the norm W1, you will find the top principal component.
If I look at it like, if I want to look at the gradient of this, right, like it seems like this is missing like a factor of W. So do you know like why, like,
it's missing?
I mean like the rule that you wrote at the bottom.
Yeah.
It's not exactly the gradient of that term, the argument term. So is it like some reason why?
Okay. Tell me why? Because the way I think of gradient, there are two terms here, right? There's a product, and so I can take a derivative of the first one. This I don't need to care about. When I take a derivative of this, I'm left with y, and then y multiplies by the second parenthesis, which looks just like this, and that will give me that.
Oh, but shouldn't the whole thing be multiplied by W? I thought. Okay, maybe my calculations are wrong. But so this is exactly the gradient. This is what you're saying.
This is deriving by W. That way.
Oh, the derivative restricted W. Okay, yeah, I got it. Yeah, I got it. Yeah, my bad.
Okay, so I take a derivative, I get rid of y and y.
Yeah, okay.
Okay, all right. And then there is a plus and minus depending.
So is it actually true, like, then neurons are actually doing like gradient-based learning? Like, is that what we believe?
Well, so we don't know. When you look at the actual neurons, what you see is that it's true that the more correlated the input and output are, the stronger the synapse.
Okay.
That is true. But the details exactly, whether it's exactly a correlation or pass through some nonlinear function or what the normalization is, that is open to debate. Okay, so people have proven, although it took a very long time, I think the conclusive proofs of convergence, this algorithm, they actually appeared in the last decade. But they have proven that if you run this algorithm, you will obtain the top principal component. Now, you were asking me, okay, biologically, is it true? Is it, so I actually, okay, sorry. Before I do that, I just want to rehash and summarize what we did here, because this will establish a template that will follow again and again. So it's worth going over what we did again. Okay, so we started with an optimization problem, right? That was the sum of the reconstruction error. And we turned it into online optimization. So every time step T, we solve two optimization problems, one after another. First, we keep W constant. We optimize with respect to Y. Second, we keep Y constant and we optimize W, right? And then we get this two updates, one for Y, which gives you the output of the neuron at that given point in time as a weighted summation of the input, and we update W so that it can be used in the next step, okay? And this, of course, all maps onto the neurons, and it doesn't look crazy. The learning rule is local, that W depends only on the activity of the two neurons that synapse connects, okay? So that's the general template. We'll follow it again and again to derive progressively more interesting and more complicated algorithms. But that's the basic approach, from optimization problem to online algorithm to neuronal model. This sometimes is called normative approach because it starts with optimization problem. And the beauty of that approach is that if you do this and you have an optimization problem for which you know what computational task it solves, then you have an idea of what the neuronal model will do in the online setting, right? So for example, for this kind of objective function, we know what the closed form solution is, right? That's the top eigenvector. So we know that no matter what kind of data we throw at that neuron, what kind of acts, we know what the output will produce without any numerical simulations. There are open questions, offline, you go to the online setting and so on, but that sometimes creates difficulties. But in general, this gives you a very good handle on what that algorithm does, even in the online setting. Okay, so we'll do this again in a bit. But before we do this, I'm going to show you a biological test. So you were asking me, is it really true that the learning rule is like this? So learning rules are hard to study because typically you can only just look at one synapse of a neuron, and there are thousands, as we discussed. So I'll look at a slightly different situation where we actually know all the synaptic weights of one neuron, and we know all the input activity. We know all the access and the synaptic weight. So we can actually test whether the synaptic weight vector is the top eigenvector for that system. This is part of a brain of a fly larva. So it's fly larva because it's a very much simpler brain than ours. So we can actually reconstruct the whole circuit. It's called the connectome. And we also can figure out what the weights are. So there are 21 neurons that sense different odors. Okay, so this is the olfactory system of the fly larva. And each 20 of the 21 neurons have different specificity. So these are the names of the 21 neurons. And these are different chemicals that were presented to the larva. And then they recorded which of those neurons became active in response to each chemical. So this is kind of like a response function of those 21 neurons to different odors. Okay? And then all those odor receiving neurons, they project them to this one neuron that is called eye. And we also measured the synaptic weights. Well, we neuroscientists in this paper measured synaptic weights in each of those connections. And then what we did, we compared the synaptic weight vector shown in blue from each of those neurons with the loadings of the top principal component of this data matrix. Right? So just like was said here, you can form a covariance out of this and then find the top eigenvector and then compare this, that's in green, and you compare this to blue. Kind of works, okay? Now, there are a lot of caveats here from the biological perspective. I'm not going to go into details, but it's important to keep in mind that this should not be oversold, okay? This is not a proof that this is correct. This is just a sanity check, okay? So that what you get is in the ballpark.
How were the individual neurons measured? Were they able to measure them at the same time, or were they like measuring one neuron?
That's a really good question. In this case, they were able to measure them all at the same time because recordings were done using optical techniques where you see all the neurons in the microscope at the same time, and then they put a chemical that reports whose optical properties change with the activity of the neuron. And that's why they can see all 21 signals at the same time. Okay, so now that we know that this kind of works, we get emboldened by our success. And why is it that we just get the top principal component? Why not get all of them? I mean, if we don't want to be, Mr. One-dimensional, right? We want to have multiple principal components to do something interesting. So, okay, let's get to work, right? We already have the template, right? We write down an optimization problem, okay? It's just like the old one where it's the reconstruction error, just like an autoencoder, right? But now y is not a scalar, yt is not a scalar, it's a vector, because there are multiple output neurons, each reporting different principal component. And these are the elements of the vector yt at each time point. And w is not a vector anymore, it's a matrix where each row is the loading of the principal components. Okay, so it's all of them are projecting x onto w. And you want to minimize this reconstruction error, of course. How do we solve it? Let's just take the derivative with respect to w by gradient descent. And so you can see, sorry, first we take a derivative with respect to y to figure out the activity yt. And we get two terms, right? One is the product of the matrix w and the vector x. That's easy to implement biologically, right? Because the elements of that matrix could be just the synaptic weights in this feed-forward network, and they multiply the vector x, and you get the inputs to this neurons. The second term can be implemented similarly, where this lateral synaptic connections, right, because they connect y to y, are the elements of the Gramian vector of w, right? So you compute this product of matrices, you have one matrix, and elements of that matrix are represented by these synaptic weights. So great, great. But the second step is also very important, right? We need to learn those w's from data. So we need to derive a learning rule. So let's take a derivative of this with respect to w. And that's where trouble appears. Okay. Can anyone tell me what the trouble is?
The outputs of a lot of neurons are not just.
Say it louder, please.
So you need the output of many neurons, not just.
Exactly. So remember how I made this big deal of this Fabian term, where the weight of neurons, a weight of a synapse between neuron I and J, that's why I kept all the subscripts here, is dependent on the product of the activity of yi and xj, which is perfectly fine because that synapse can get those numbers. But then there is the second term, which requires for the synapse between neurons I and J to know the activity of all the other neurons in that place, which is not physically possible. Okay, and with those like specific weights, W, J, K, how is it going to get them? That's crazy. And this is just only the beginning of our trouble, because this is the learning rule for the feed-forward weights. To learn the lateral weights, we don't even have a learning rule. What you would have to do is to adjust the W, then compute the gradient, and then take the values of those, the elements of the gradient and put them through, which is just like so biologically implausible. We should probably just go home. Okay. So that's the trouble. And it has been known since early 90s that if you want to have an algorithm that is designed from a principled objective, like an autoencoder, you can do it. You can adjust it by gradient descent. But when you implement it biologically with a single layer neuronal network, you get non-local, non-biological learning. Right? Sorry. Okay. Some people say, okay, I want to model neurons, so I better have local learning rules. So quite a few people did the following. We don't like this term, so we're going to play with the algebra here and come up with some kind of phenomenal, I would say heuristic learning rule that numerically we can show actually works and do something like PCA, but because it's not derived from principal objective function, we can't really prove that it's always the case. Question?
kind of the problem happens because we're sharing this W across multiple neurons, right?
We're sharing, we have to share Y. Right? I mean, each neuron, so each neuron receives a vector of W, which is basically the raw vector of the W. Okay, but yeah, the trouble arises from that cross term, not cross term, but the quadratic term. Let's say. Right? That's where the trouble sits. The trouble comes from there. Okay. That term is important, by the way, because if you didn't have that term, then all the neurons will learn the top principal component because they would use the same learning rules and they see the same data. So they will become redundant. So you need to have some kind of lateral interaction that implements competition. But this isn't that. So this was kind of the situation in the field until about 8 years ago when we got into the business. And I was very troubled by this. When I actually learned that there isn't a solution to this, I was very upset. It's like, what's going on here? And so I spent a lot of effort trying to come up with an alternative. And I think we now have one. And we call that similarity matching approach. And the idea is basically to keep the same template, to write down an optimization function, you derive a network by using online learning, but to start with a different objective function. Okay. So I didn't know that at the time. So I actually came to it through a very winding path, but I should have known, as lawyers say, that there is such thing as multidimensional scaling. And this is a method used in statistical learning to project a high dimensional data set onto a lower dimension while preserving the similarity between data points. Okay, the specific version is called classical multidimensional scaling. There are many others. But the point is you describe the similarity of the data by their input product or their scalar product you like, and you try to preserve it in the output data. But the dimensionality of the output is actually smaller than the dimensionality of the input. And so that's how you find that latent subspace. Okay, so that you have all this pairwise similarity of the input data, which is written here in the matrix T by T. And you want to approximate it by another matrix T by T, which contains all the similarities of the output data. Okay, but you hope that there is a low dimensional manifold in linear subspace in this case, where most of this data lives. And so you can capture it by low dimensional Y. Okay. And in fact, you can prove that the optimal solution of this data, of this objective function, is indeed the principal subspace of this data similarity matrix. Okay, so for top principal component, principal subspace is just the top principal component. For all the other subspaces, it's the same as the principal component up to an orthogonal rotation, right? So it's the same subspace, but you can choose your basis up to rotation. Okay. So that can actually be proven by just you write down X and Y in terms of singular value decomposition, and then you do a little algebra and you prove that. So okay, now we're in business, right? We have an objective function, and that objective function gives you pretty much the same thing we wanted to get before, which is the latent linear manifold, the principal subspace. We just have to derive an online algorithm and map it onto neurons. Question?
I'm just confused how this works when X and Y have different dimensions. but maybe I'm misunderstanding the indices.
Yeah, so, okay, maybe I should have made more explicit. I'm kind of a little sloppy with the indices. So X has two indices, which is, I, J, and all those, and T. Okay. Xi is an element of the input vector at the ith position at time t. So you can also think of X as being a matrix where this is like a channel and this is a time point. Okay, so at each time point you get a vector which is indexed by I or J, and then at a different time point you get T or tau. Okay, sorry about that.
And yeah, okay, and then we get T by T matrices when we take the.
Exactly.
Okay.
So because now you take this and you compute in the product, and then for every pair of those columns you can compute this and write down into this big similarity matrix or Gramian or kernel matrix, as they would call it in machine learning.
Okay, thank you.
Okay. That's why, because both of these matrices have T by T elements, that's why you can try to match them. So this is like a, in the reconstruction or autoencoder approach, you minimize the reconstruction error. Here you minimize the mismatch between similarity matrices. Okay. So we're about to embark on our program and derive an online algorithm. But thinking about it for a second, you probably stumbled because this isn't an objective function that looks nice to an online algorithm, because in the online algorithm, you compute the output YT without having access to most of the data except for XT. Here, it's not the case. T and tau from all the time points are entangled with each other. Okay, if you're doing it offline on the computer like a old school statistician, it doesn't matter, right? You still compute the eigendecomposition. But how are you going to do this online? And so what we were able to figure out is that there is a simple algebraic trick to circumvent that problem. And here's what I'm going to explain what that trick is. Okay, so this is the objective function that we have. And by expanding the square, you find three terms. The quadratic term, the quadratic in X term doesn't matter because it doesn't depend on Y, with respect to which we're optimizing. But the next term is the cross term that has two X's and two Y's. Okay, so how are we going to optimize this online? Well, it turns out that we can rearrange the factors here so that two factors that have subscripts tau can come together and be summed over tau. And that sum is actually sample covariance, right? Because we're taking data samples at the same time and we're computing their outer product and summing over time. That's covariance, which we'll call W tilde YX.
Are you missing the term for the YY?
I am. I'll get to that in a second. So what happens here is that at every time point, once we've seen enough samples, the estimate of the sample covariance doesn't change much. Remember how we used WT minus 1 in that OI algorithm? Well, here we'll use this sum from the previous time step. Then we just need to optimize with respect to this Y. Okay. And for this term, it's very easy to do because when we take the derivative with respect to Y, this is just the product of the matrix by a vector, which we can do with our favorite feed-forward network. Remember, it was in blue lines. But as correctly pointed out, there is also quartic and Y term, but we can perform the same trick with that term. Now, just do it here. Okay. So let's see. So we have minus sum over t, sum over tau. That's how I call them. Y t. Y t y y tau, and then I have y tau transpose y t, and then I do the summation over tau. I will call this M tilde, or I think it's called, wait, WYY, sorry. Okay, so that's what the quartic term looks like. When I differentiate with respect to Y, I get this linear term. So now I can solve for yt at any given time point by iterating this expression. There is a slight issue with the normalization here, but don't worry about it. It's straightforward. Most important is that this iteration can be implemented by a biologically plausible circuit where this matrix vector multiplication is implemented as before by feed-forward synaptic connection, and the lateral connections are implemented by this matrix vector multiplication, just like before. But when we write down the learning rules, which are just updates of this WYX, WYY, because these are just covariances, they're much simpler and they don't have the summation that Doc does before and made those learning rules look.
Is there a way to weight similarities between certain features more strongly than similarities between other features? Penalize them more heavily, or yeah, penalize differences more heavily, I guess.
Yes, so I would think so. You insert some kind of diagonal matrix there. And I think you will do that. I don't think I ever wrote this down, but yeah, that seems possible.
Yeah, I think like in certain contexts, you might care about similarities between some features more than the others.
Right. So yeah, so then that would be dynamic, and that you would use this as some kind of weighting. So that will require something. I think it's possible, but I've never written down a circuit like this. If you want to talk about it offline, I'm happy to do that. Yeah, so again, I wrote down all the subscripts here to emphasize the fact that the update has this fabian term and this other normalization term, which again requires only Wij instead of the sum of all the guys, and relies only on the activity of that neuron I and nobody else.
But the normalization is dependent on all previous time.
Yeah, so that may seem like a complication for online, but it can be solved at the cost of introducing one scalar variable per neuron, which will keep a running sum of those and then update that. And the neuron has plenty of mechanisms to do that, like, concentration of calcium, gene expression, phosphorylation. So this, neuron is a factor. And it's not hard for it to keep one scalar variable. I mean, it's already holding 1,000 of synaptic weights in memory. So one more scalar variable is not going to break the memory. Yes, you need that.
Oh, yeah.
Full online.
I just one more question. So the normalization is only so that the units will be the same, or is there something else behind the normalization?
For one neuron, it is just determining the learning rate. For multiple outputs, I think you actually need it for the correlation, but I'm not 100% sure. I'll need to think about it. Okay, so basically what we achieved now is we now can discover this latent linear manifolds by performing this multidimensional scaling, which is just like PCA, recovering the top principal subspace. But now with totally biological plausible local learning loops. So that's great. We can pat ourselves on the back. But of course, you already know that just performing linear computations doesn't get you too far, right? PCA, it's great in some situations, but most interesting cases, the latent manifolds in the real world are, of course, nonlinear. So linear subspace won't discover. And of course, that corresponds to having nonlinearities in neuronal network. So perhaps it doesn't come as much surprise that what we're going to do next is to modify our new objective function, the similarity match objective function, by simply requiring that the output is non-negative. That's it. That's all we need to do. How did we come up with it? Well, it was actually inspired by biology, because an output of neuron can be measured, for example, by its firing rate, the number of spikes per second. Well, the number of spikes per second cannot be negative. The lowest you can have is 0 spikes per second. That's fine. You can have 100 spikes per second, or anywhere in between, but you cannot have negative number of spikes. So knowing that, I just said, okay, let's just require y to be non-negative. And amazingly, this little constraint changes the nature of this objective function radically. It doesn't find the principal subspace anymore. And in fact, for generic data, it's not polynomial complexity, it's exponential complexity. This would be known as like some kind of symmetric non-negative matrix factorization, something like that. And but the thing with those complexity theorems is that these are worst case scenarios, okay? And we want to just get work done in practice. So for many kinds of data, it's actually possible for us to understand what the solution of this objective function is. For example, when the data comes in well-defined clouds of data points that can be clustered, this objective function actually clusters. Okay, so let's try to see this intuitively. So, suppose we have this kind of stimuli, okay, that are break down into two groups. So it's known, for example, that in the part of the brain called IT, the neuronal activity vectors when you see cats are more like the neural activity vectors when you see dogs than the neural activity vectors when you see trees or flowers. And the same with trees and flowers. They elicit activity vectors that are more like themselves than the animate objects, okay? So given that, can we now have a circuit that will classify a stimulus into animate or inanimate? In fact, we can, and this tells you how, right? That if we want to find a low rank matrix Y, here we just give it back 2, that that is trying to match the similarity of this input, that is, match this matrix of similarities under the constraint that y is non-negative. What are we going to do? Well, red is negative numbers, so the best we can do in terms of matching is to set them to 0. These are positive, and so they will stay positive just to make a connection with clustering. If we limit the highest y to be 1, then you will just put 1s. And then if you have a similarity matrix like this, what kind of an activity vector does it correspond to? The vector y would be like this in response to the flower, same in response to the tree, and the opposite neuron would turn on for any stimuli. Okay. So this objective function can in fact cluster this kind of easily clusterable data. Now we need to derive a circuit, and we know how to do that. We follow our template, we write down the objective function, we discover this algebraic trick, and then we derive an iteration that computes yt on the fly as a function of xt. And it's just like before, 2 matrix vector multiplications, except now we have to project the output y onto its domain, which is non-negative. And so we just have a rectification here. And this, again, can be implemented by a neural network that is even more biologically plausible than before, because after weighted summation here in each of the neurons, we have a linear rectifier. So these are just simply ReLU neurons. And the learning rules are the same as before, because mathematically it's all the same. Constraint doesn't matter for the learning rules. And now we have a neural network with biologically plausible local learning rules that now does clustering. So we can tell cats from dogs or cats and dogs from plants. You with me? Can we understand how this network works? So let me try to do this on a more accessible data set. So for that, I took a data set, 2-dimensional data set, where this data points were generated by a mixture of Gaussians. Okay, so the 3 clusters, blue, green, and red. Of course, the network doesn't see the colors.
Yeah, sorry. Can the data points themselves be negative? Is that like an assumption that?
Yeah, so, okay, very good. That's a good question. So if the inputs are all positive, then rectification doesn't matter, right? Because then you don't do anything. So actually, for this algorithm to have teeth, you want the weighted sum sometimes to be negative and cut it off.
Is it possible biologically for the inputs to be negative, like in some sense negative?
Yeah, so that's a really good question, because often it's not. Okay, so what you need to do, you need to take into account that there is this lateral connections that are inhibitory.
Oh, okay.
In this case, well, there is a biological plausibility reason called the Dale law that we wanted to respect here. And so these are the same lateral connections, but implemented indirectly through this interneuron. Don't worry about that. That's a minor issue. The point is that these are the minuses that flow in. And so because of that, you can get a negative.
So like the inhibition neurons are removing some of the
That's
charge.
right. That's right. Yeah, so the data is like this, and we want the algorithm to cluster it into these 3 clusters, obviously, without seeing color. And we just fed those in the order indicated here. And it turned out that the algorithm produced this output, okay? So This algorithm has never seen any data before. Okay, so it's W or initialized as 0, and then you try adding this W vectors as you see more data and adjust them. And despite that, in the online setting, it produces this clustering result because one of these neurons, it doesn't matter which one is blue, the other is green, and the last one is red. And so the blue neuron activates first, then the green one, and then the red. So if you read the output of those neurons as assignment indices to the 3 clusters, you will get the clustering of the data set. How did it happen? Well, it's intuitively, it can be intuitively understood. So each of those neurons has a synaptic weight vector of impinging on it, which is shown here. The green neuron is this weight vector, the red one, the blue one, okay? Of course, they have to learn those vectors. But once they learn, what happens is that the data vector comes in, say the green one, gets projected on each of those vectors. And then there is a competition between them because they suppress each other. And the one that wins this competition is the one whose projection is highest. So the green one wins. And that's why that green neuron is active and all the other ones are silent. Where do those W's come from? Well, as before, every time you see a data point that is a little bit off from W, there is a learning rule that pulls that W in the direction of that data point, just like in the OS algorithm. Okay? And so that's how those W's get established. And then you compute the clustering. And another interesting aspect that you might think is a bug, but is actually a feature, you will see that, is that one of the points is attributed to 2 clusters. That's the point number 13, which if you don't see the color, you actually don't know if it should be red or blue. And neither does algorithm. And so it shared it between the red and the blue cluster. So it's soft clustering. Please.
Just another question. So you said the W's are initialized to 0?
Yes.
But don't they all, isn't the update the same for everyone if it's initialized to 0?
Okay, very good. So what we do is so the way we do it is like that. The first time when they're all zeros, you present the first data point, okay? And if no neuron is active enough in response to that data point, then you set the synaptic weight of that neuron to be equal to that data point.
And that is more plausible than beginning with something that is non-zero.
You can start with the random W's, but then you will not do it from the beginning. There will have to be a warm-up period where you adjust to your data set.
I mean, like biologically, what would be more plausible?
There are arguments for both. Genes could set up the original weights to be close to the data, or it could be that there are connections that are formed as trial and error and then proven. Both of those things exist.
Is there any change if I change the order in where the colors are like inputted? Because you're first.
Yeah. So which color goes first doesn't matter. But I chose the worst, I think, case where you just put one cluster first and then the second and the third. I think that if I intermix them, it would be easier for the algorithm because it gets a more fair statistical distribution from the beginning. So I think I had the worst case scenario for the algorithm, but it still worked. Is that what you're asking?
Yep.
Yeah. Okay, great. So we can do soft clustering. That's not what I promised you. I promised you nonlinear manifold learning, which is much cooler, obviously, right? But it turns out that we're almost there, okay? Because, so this objective function looks a little bit different from what we had for clustering, but it's actually this is a mathematical necessity because for this particular objective function, we can prove that if your data comes from a circle, right? So all your data is distributed uniformly on a circle, then the neurons would learn this pretty looking clusters, okay, shown here. There would be the receptive fields of those neurons, where they respond with this kind of activity in response to the data at the corresponding points of the circle. But numerically, you would get the same result from the previous objective function. It's just for this one, we were able to prove this fact, okay? And this is a numerical simulation with a similar network where, you just have the simpler value neurons and you throw data from a circle to it, and this is the kind of responses you get from neurons of different colors, okay? So this is basically soft clustering the data, but importantly, right, those clusters that neurons represent, they overlap. Because they overlap, the output preserves the neighborhood relationships that are in the input coordinates of the circle. So that network effectively learned the manifold, right? If you present another data point from somewhere you haven't seen before, it will be captured by just the right neurons so that that representation will be similar to the representation of the nearest data point on that manifold, meaning that we learned the manifold. So that's a big deal because we now can start solving really interesting problems. For example, if we don't have all the data on the circles, but we have this two half moons or something, it's called two sets of data, okay, we can also learn them with our objective function. There is a slight tweak that is needed because it's no more circularly symmetric around the origin, and so we have to represent similarity by the distance rather than by the inner product. But it's a similar circuit, and each neuron learns a different neighborhood of each of those half moons. The neuroscientists are really excited about this because there are neurons in the brain that in the part of the brain called the hippocampus that actually represent space this way. Each neuron is responsible of its own neighborhood, and the neighborhoods overlap. So this is like the real animal, real rat that is riding around this labyrinth, and different colors show activities of different neurons. And it looks just like these neurons that we're talking about here that learn the manifold, okay? And then, of course, once you learn the manifold, you can learn difficult computer science or computer vision problems, right? Like classify faces. As I mentioned to you before, each face lives on a manifold in this high-dimensional, million-dimensional pixel intensity space. Those manifolds are highly entangled, okay? They never overlap. It looks like they overlap because this is a projection on 2D space, but they never really overlap in this million-dimensional space. And you may want to classify the faces by pulling those neurons, those manifolds apart. That's how people sometimes think about what the deep learning network does in the brain. And if you can do this without tearing the manifolds and preserving their neighborhood relationships, you can pull them far enough apart and just classify this linearly based on a single label, for example. Okay, so can our network do that?
It's a good question about IT. Is IT generally thought to perform some kind of classification?
Yeah, so in IT, the representations are like for those dogs and cats, right? They're based not on the pixel similarity, but on the cognitive identity, semantic identity, right? Like dogs versus cats and so on. So, but somehow you get from the pixel representation where those like two faces can be look more similar to each other in the pixel space, if both people are looking in the same direction, then the face of the same person looking in different directions, which in the pixel level looks very different. Okay, so how do you preserve identity? That could be one way to look at it. And so maybe you can use our algorithm to do that. Well, okay, disclaimer, we cannot do this for real problems like face squares, but we can do it for toy problems, right? So for those half moons, we learn neurons that each of which represents the neighborhood of one of the moons, but this 15 are from the first moon, this is from the second, and in purely unsupervised fashion, if we stack this network 6 times, we can eventually tear them apart, and this is even more entangled scenario. By reducing the number of units in 2 at every layer, we eventually get to the classification where the 2 manifolds are pulled apart. Why do we need so many layers? That's just because we wanted to do it in unsupervised fashion. Okay, if you have supervision, if you just give me 2 labels, I can do it in 2 layers. The first layer will compute that neighborhood representation, and the second one will tell you which 15 neurons are first half moon, and the second is the other 15 is the second half moon. And you see this little notch here in the similarity matrix that tells you that this should be possible. But of course, without supervision, it's very hard to find that one direction because its Laplacian eigenvalue is very small for those who know. And so that's why we had to do it in 6 layers. But with supervision, you can do it in 2. Anyway, so this is how far we could get with this kind of manifold learning. Any questions?
Do you ever do something similar with like sparse? Like, does it, including sparsity, help? Like, if you start with many neurons and then you sparsify it down, would it kind of find a better solution with fewer layers?
Sparsify meaning
like, so I think do you know the lottery ticket hypothesis? It's basically like if you have many neurons, you're more likely to find you're kind of like you're better conditioned to find the true function because you have many more lottery tickets. So it's kind of like you always have the like one of the neurons is kind of close to the true function. So you have to like gradient descent less. So one of the reasons people think like starting very wide with your neurons and then sparsifying, even though you still end up with the same number of neurons, you can actually like it's a easier optimization problem. Do people ever kind of study it in this perspective?
So that's a really good question. In neuroscience context, I think people would refer to this as random projections. And, you know, there are actual places in the brain where something like that seems to be happening. We have not gotten much knowledge out of it before because we can actually hear the idea is that you basically like learn the directions based on the data. So you're kind of trying to adjust. But that costs time. So yeah, if you have a long, you know, stationary data set, you eventually learn. But what if you want to do it like, you know, after a few examples, like single shot learning? So that's when your scenario, I think, is the right one. So you make a lot of random projections and you try to find the one that gets it right.
Yeah. And then you kind of like
And then you
initialize there.
magnify it.
You initialize there, yeah.
Yes, exactly. So right now we have something in progress. So that's actually a collaboration between my group and our Simoncelli's group, where we can do that. So we have basically random projections, and then we have automatic gains. in those neurons. And those gains can be done in can be adjusted in real time. They don't require long, slow synaptic learning, which is kind of what happens in real neurons. In addition to slow synaptic learning, there is a fast dynamics that, remember, I had on the first slide, but we never actually used it in this talk. But it's there. And that's what you can use to do exactly what you said. So I think that's exactly the right intuition, and just work in progress. Okay. So looks like it's 4:50, so I have 10 minutes left. I have one more topic, getting back to supervised learning. So you want me to stop here, or you want me to do this last?
It's up to you. If anybody has questions on the other parts, yeah, we could do more. Yeah,
you could.
You got 10 more minutes.
All right. So I said, okay, most neurons are unsupervised, but of course, in the end, you do have some instruction. You have rewards. Your parents discipline their kids sometimes. So it can happen. You try to imitate a song or something, right? So there is some supervision. So what can we do about that? And we did it first for the simplest case when you have a two-layer network that is really well understood, right? So you have the input units, the output units, and then you have the middle layer, which has fewer units, and then you have a forward pass, which you basically multiply the input data by this wide matrix, and then you multiply the gain by tall skinny matrix. And you can solve it by backpropagation algorithm, where you have a backward pass, of course, where you're supposed to have this target y. You compute the difference between your prediction of y and actual y, and then you shift that error scaled by the synaptic weights Vy from this layer to update the synapses. And that's, of course, where backpropagation becomes non-biological, because who will carry this information to all those synapses in a specific fashion and collect along the way the weights of those synapses? Okay, if you run it on CPU architecture, you're doing great, but how do you do it with real neurons? That's where trouble emerges with backpropagation. But there is a saying in Russia. I'm trying to translate it to English. If something is forbidden, but you want it very much, then it's allowed, right? Okay, don't quote me on this. Okay, so we tried to do this here. This is the work that was spearheaded by Servaz Kolkar, whom you've met. And the basic idea is the following. If only we could first multiply the label y by Vy, so that we have this low-dimensional representation A that we could match to the lower dimensional projection of xb, then use that mismatch to learn the x's, then maybe this could work. Okay, so it's almost the same update as we want in backpropagation. But that may sound crazy, right? Because wait, but this error is stored in this neuron A. How will it get to the synapses and pinge on the neuron B? That's not going to work unless A and B is the same neuron. Remember how I said neurons have compartments? And those compartments sum the inputs separately before combining them?
And actually, this is a picture of the most numerous neuron in your cerebral cortex, which is called the pyramidal neuron. And in that pyramidal neuron, it gets inputs from your observation, sort of feed forward, and the feedback, modulatory inputs or instruction, onto different parts of its tree. So it's like a tree, it's like an arbor, and this is the root system. Both of those parts get input to different kinds of inputs. And the neuron is known to sum them separately before combining them together. So maybe this unit A, where you compute the difference, could be here, and this unit B could be in the same neuron. Okay? And then you somehow signal from this unit down here and adjust those synaptic weights. Can this be? Well, in fact, that's what happens. So the output, the main output of the neuron comes out of here, axon comes out, and there are spikes produced here. But in addition to that, there is an internal signaling channel called the calcium plateau that communicates between these two integration compartments. And in fact, these people have found that the synaptic weights on those dendrites get adjusted based on the correlation of the upstream activity and the calcium plateau, and not the outgoing activity of that neuron. So it looks as if this neuron uses this error with those inputs to adjust those synaptic weights, just like you would need to implement this algorithm. Of course, there is a slight difficulty with the minus, because you have to subtract what is coming from here from what coming there, even though, currents usually add, don't subtract. But you can overcome this by this inhibitory neurons, which turns plus into minus. So this all actually can work. And people have actually noticed that calcium plateau can play the role of this mismatch, especially this work. So what did we do? Well, we showed that we can actually derive a network with the normative approach, starting with the principled objective function, which is the one that I showed you before, and then doing some optimization, gradient descent, and then coming up with the neuronal network. The advantage of that approach is that we know what the network is going to compute for any input data. We don't have to rely on numerical simulations.
I don't know if this matters for biology, but this reminds me just like philosophically of like a GAN or something, that like you compare the outputs of two networks and like you try to minimize the difference. Is there like a biological GAN or something?
Yeah. Yeah, I mean, it's much simpler because it's just linear projection. But yeah, it's all about like finding the mismatch and minimizing. That's the idea.
So it seems like the output is very different, or is different from the instruction, right? So the output goes in one direction.
Exactly. So the output is this projection onto this intermediate subspace. It's not y, it's Vx.
But how is this coupled then?
How is what?
How is this coupled? Because
so it's adjusted through this projection. How do you get to y?
Yeah, exactly.
You need another layer. I'll show you.
Okay. Because in the end, you need
exactly.
kind of back problem.
Exactly. So this is not the whole story.
Okay.
Yes. Yes. But what we did, we basically, now that we are like experts in this similarity matching approach, and we followed the same template. We started with objective function. I'm not going to go through this since we don't have time, but we ended up with a circuit which is derived from the objective. So it's not just drawn heuristically, it's actually derived. And the learning rules that turn out to be all local because that's biologically possible. And then we have this inhibitory interneurons that are crucial to make this work. Okay. So the amazing thing is that it looks a lot like a cortical circuit. And so this actually is derivable from a principal objective, yet looks a lot like biology. And that's why we're excited about it. Of course, there is this question, because the output carries just one projection, we need two. And so that's why Siavash did not rest at this, but he spearheaded the next paper where we were able to stack together those layers. And then you can put this output through the next layer, which encodes another set of bits. So you can actually stack those networks to do something like a deep learning. It's not really error back propagation. It's more comparable to what people call the predictive coding. I don't know if you've heard. It's one of the attempts to make deep learning more biological. Okay, but it still has some major biological inconsistencies. And what we basically have is normatively derived predictive coding with fewer biological violations. And it works as well as the regular predictive coding, even though it's more biological. Okay. So that's basically all I wanted to tell you. And in summary, so we developed this theoretical machinery that allows us to derive biologically plausible machine learning algorithms for learning linear and nonlinear manifolds in unsupervised and even supervised setting. There is some similarity with biology, so we're happy about it as we're neuroscientists. But I think that something that we realized that we didn't understand when we embarked on this problem, on this direction, is very interesting. When we started doing this, we said, okay, we want to do machine learning, but in a biological plausible way. So because we it's like fighting with one arm tied behind your back, right? Because we have to respect biological constraints. We're going to have algorithms that account maybe for what happens in the brain, but we're always going to lose to generic machine learning algorithms that don't have those constraints. But it turned out in the end that it's not quite so, that quite a few algorithms that we derive are competitive with general machine learning algorithms that do not take those biological constraints into account. So for online algorithms, for PCA, for example, we are as good as the state of the art. Also, manifold learning algorithms, they're kind of hard to compare, but they're pretty good. So now I would say that these biological constraints should not be viewed as roadblocks that make your life difficult. They're more like guardrails that point you in the right direction, because you know that the brain can actually do artificial general intelligence, right? So there must be an algorithm that respects biological constraints and does AGI. And if we take those constraints in, we are doomed to follow that restricted path that will lead us eventually to AGI. Okay, and on that note, I would thank all the people involved in that work. I was very privileged and lucky to work with this very talented scientist. Thank you very much.